So before we start with the first spotlight, I'm just going to give you a short introduction so you have a better overview about the workshop and what's going to happen today. So this is the organization team. So on behalf of all the organizers, welcome. It's great that a lot of people came here and are joining the workshop. Yeah, so also a big thanks to the program committee. So we had quite a intensive support from a lot of people who reviewed papers. So I'm not sure if some of the reviewers are here, but in case you are, thank you. So applause to the reviewers. Yeah, so some statistics. So just for a short overview, so we had 22 submissions and we accepted 13. So quite high acceptance rate, but on the same hand, I would say also the quality of papers that received was quite high. So thanks for all the submissions. Sorry, that was from sorry, I mixed up the numbers. So that was from last year, and this year we had 36 submissions and 18 were accepted. So last year we had quite nice quality of papers, but I think this year was even better. And we also have now this additional track with extended abstracts. So just in case you missed it this year. So also if you have an kind of quite early idea in an early stage, you're welcome to submit an extended abstract. So this is also relevant for next year. So you're invited then to have a poster and interact with all the other participants of this workshop. Yeah, there's also the challenge. Lata already mentioned it. It will be in the afternoon then. And here you have the overview. So we have now swapped the first keynote with the spotlight because I think we're still waiting for Maya to join, right? Yeah. But nevertheless, we have then the second keynote with Summit, then a short coffee break, then another round of spotlight presentations and keynotes, and then a lunch break from approximately 12 to 1 p.m. And then in the afternoon, we start with a keynote from Radu Tudor Ionescu, and then we have the whole challenge track. And in the very end, we have the poster session. I think the poster session is then located in the other building, or? But I'm not sure. We will let you know. We'll figure it out in the meantime. Yes, it's in the Arch building. I should have looked at the slides a little bit better before, I guess. Yes, and you can have here the QR code. We will show it also kind of in between the talks. So it's always nice to get feedback and to improve the workshop. So in case you have feedback for us, you either approach us personally, but if you want to do it anonymously, yeah, here's the QR code. So yeah, let's start with the first spotlight. Mathis. You sent a PPTX, right? Is you know, sent a splat post, right? Yeah. Yeah, here it is. Yeah. Yeah. Right.
Yeah, thanks for coming, everyone. Kind of funny that I get to kick off the workshop. Hello, my name is Mathis Kruse. I'm from Hanover, Germany. I present today Splat Pose and Detect Pose-Agnostic 3D Anomaly Detection, which I wrote together with Marco Rudolph, whom you may know from his normalizing flow papers like Differnet or CS Flow, Dominik Voivode, and Bodo Rosenhahn. Yeah, whoops. Test.
Test.
Did I rip it out? Test. Now it's working again. All right. I'll just be more careful. Well, it's motivated by previous data sets. As we all know, we train them mostly in most papers semi-supervised, so we only train on normal data. But as we see in these two examples with MVTech AD and the Visa dataset, which we may all know, there are very tight constraints on both camera and object pose. So on every image, it's the same object pictured from exactly the same pose, very tightly constrained. At last year's NeurIPS conference, a new dataset came along, the MAD dataset, so multi-pose anomaly detection. And it features these Lego objects, and there's of different poses, as you can see below. But during training time, there's also pose information available, so we can incorporate this prior information. But at testing time, when a new test picture arrives, there is no pose information, and we have to decide, irrespective of pose, whether there's an anomaly present. So irrespective of pose, we want to detect those anomalies. How do these anomalies look like? So as I said, these objects are arbitrarily placed before the camera. And in this example with the swan, there are several different defect types like missing bricks, as you can see marked right here. And also in the second example, the same brick is missing, but obviously from another pose. So depending on pose, it's much more difficult to find whether or not this brick is missing. Other anomalies also include discoloration or excess material. So what do we try to do with splat pose? Well, we want to use these multi-view training images to build up a point cloud or Gaussian splatting-based representation of our good objects. And then these query images on the left side come in. As you can see, this pig is missing an eye in all three of these poses. And we want to align our anomaly-free representation to these query images, and then pretty much go from there and are able to compare to our rendering and generate these anomaly maps. And irrespective of pose, we are able to find this missing eye in this case. How do we learn this pose invariant normality? Well, we use 3D Gaussian splatting for that, which you may already know. As input, we are given these multi-view images with their pose information. From that, we can build up this point cloud representation, which essentially is each point in this point cloud is a multivariate Gaussian, as you may know, with stuff like a rotation and scaling factors, density value, how much they contribute to the object, and also RGB values. Given this point cloud from a given camera pose, we can then splat these 3D this 3D point cloud onto the 2D surface and essentially render an RGB image. On the right-hand side, you can see the novel view synthesis capabilities of this, and we can pretty much render images from every possible camera pose or object pose in this case also. So how does the optimization work here? Well, on the right-hand side, we are given a test image with a small stain on the left. And we start from a coarse camera pose, keep this camera pose fixed. And since Gaussian splatting is differentiable rendering process, we can use the mixture of L1 loss and structured similarity loss to essentially iteratively change the pose of our renderings until they are properly aligned to the test image. And once that's done, we can pretty much just compare the two, in this case, using deep features, take a difference of these deep features, and wherever these features are different from each other, we get a high anomaly score on the anomaly map. For a final single score, we can just aggregate it using a maximum or an average. So one more time on the overview. During training time, we use these multi-view images to build up our 3D Gaussian splatting model. A query image comes in this case, with a missing brick. We coarsely estimate a camera pose using deep features again and a pretty much nearest neighbor from all the training images. Now, keeping the camera pose fixed, we are able to differentiably render images of our object, compare these renderings back to the query image, and then we can backpropagate to, in this case, the transformation sampler, which transforms the explicit point cloud representation. In that way, we are able to pretty much get the same rendering as the query image, but without an anomaly. In the end, we match these features to generate our anomaly map. So of course, we evaluated this on the MAD data set. And as usual with these papers, we are better than all competitors, especially better than OmniRD, which is the other 3D object-based method using neural radiance fields. It should also be said that all of these 2D image-based methods, which we all know, which work without poses, heavily underperform in this setting. And we hypothesize that our good pose estimation and high-quality rendering lead to the strong performance. Also, we are much, much faster than the only other good method, OmniRD, since it's working with vanilla nerves, which are very slow in both training and inference. We also evaluated the pose estimation. As you can see, we trained this for 175 iteration steps. And on the right-hand side, you can see a bunch of examples of our poses being estimated. So on the right-hand side is the ground truth here, and this is our pose estimation result. We also evaluated empirically on both the MAD dataset and the nerve synthetic scenes, and we are also much better than the coarse pose estimation and the iNerve, which is the basis of OmniRD. Yeah, to pretty much conclude this now, multi-view anomaly detection is a pretty difficult new challenge because previous methods don't include these pose priors. We are able to model anomaly-free objects using 3D Gaussian splatting with pretty fast training and inference speed, and also direct manipulation on the point cloud representation that we learn. At test time, we pretty much optimize our point cloud to the pose of the query images and are able to achieve state-of-the-art performance on the MAD dataset in all metrics, both detections and segmentation, a 3% gap now in detection with a 93.9 AUROC score being the new state-of-the-art. Come up to me with any questions. I'm here all day. And scan the QR code for paper and code. Thank you so much.
So if you have any questions, just walk up to the microphone and ask them.
Hello, very interesting paper. So I was just wondering, because you were showing that you have an anomaly map in 2D. Is there any way you can do a 3D anomaly map? Like, because I think that you got it from the 2D images, right? But is there any way you can actually?
You could probably map the anomaly score back to the 3D Gaussians in the sphere, probably, and then in that way get some kind of 3D map. Also, probably incorporate the density, because if the density is low, then probably further back the points contributed more. But yeah, probably yes. But it would take some work, of course.
Hi, thank you for the presentation. I have a question. After you train the Gaussian splats and you want to estimate a pose for the query image, do you have only one pose that you optimize, or you have different seeds?
I just start with one coarse pose camera estimate, and then we apply these transformations to the point cloud. So it's only one pose that I'm estimating. And also the current Gaussian splatting kernel is not able to render more than one image at once. So it's kind of hard to do more than one. But you could theoretically, like in parallel, start with several poses and then maybe find a more optimal result. But no, currently it's just one.
Okay, thank you.
A very interesting paper. Thank you very much for the presentation. Two questions. First one is, where do you see this being applied, like in real life, like for industry? That's my first question. And the second one is related to when you compare the poses to find that map, how do you align like the views to be able to tell the difference between the original view and what you have? Appreciate it very much.
In practice, you like this data set is with Lego toys, so all of the products pretty much have to be the same shape as of now. They can in some way also work with different texture, but depending on how much the texture is different, then the anomaly score also rises. But I'm trying to work on that with a follow-up. And the other question was how the pose is, how we pretty much evaluate how good the pose is. So well, we just optimize it as of now. And after 175 steps, it's usually very, very, very good. So virtually no difference in pose. But I could also use the transformations that I've learned on the point cloud and like calculate them back to the camera coordinate system. And that way also pretty much get the exact numbers of how good the pose is. So theoretically, you could just let it run and until it's like within a few millimeters of proper pose, then you can just stop. That would also be possible. All right, thank you so much.
I think it's fine. By the way, the anomaly is not better or whatever. Maybe that's intended. Maybe. Yeah. Right. On introduction. Yeah, sure.
Okay, so ladies and gentlemen, a slight change to our program. We're going to have our second keynote speaker now, who is Samit Atki. So Samit, once upon a time, used to be my PhD student at Durham, but since then he's gone on to much bigger and better things. So a quick journey through a startup, Cosmonio, is now part of Intel, and has been working, as many of you may know, in the anomaly detection community as the lead developer on the Anomaly project, as well as himself being involved in various published work in the anomaly detection arena. So Sam, I'll hand over to you, and you can take it from there.
Is it possible to use the PowerPoint app instead, not instead of the web version, or not? Okay, cool. All right. All right. Hi, everyone. Thanks for inviting me here in the first place. Good to be here. Right. Okay. Can you hear me? Okay, cool. Yeah, thanks. Yeah, today I'm going to talk about visual anomaly detection in general, but from a different perspective. But because, throughout the day, we're going to be hearing about amazing papers, amazing algorithms, models outperforming one another. But my point of view will be a bit different from an open source approach, from the tooling approach, because when you are working on anomaly detection problem, many of you probably noticed that, tooling wise, we're not as rich as the other tasks like object detection. For example, when you look at the object detection problem, there's tons of frameworks out there, like all the way from Detectron to detection, or maybe like you name it, bunch of different frameworks. But when we are working on an anomaly detection problem, yeah, we don't have that much options, unfortunately. So we noticed this gap in the field and basically introduced Anomaly, which I'm going to talk about today. Yeah, so if you're here, you probably know the visual anomaly detection problem, but it has a significant amount of applications, mostly in industry. For example, here you can see that, it's just a simple example, but by just focusing on normal examples, training normal images, we can find out any sort of abnormalities during the test time. Of course, this is a simple example, but you can see many, many similar examples in industry. This is how anomaly detection can be applied and is applied currently. And as I said, there's so many different use cases in industry, and there's like quite a bit of investment by companies as well to get like quite accurate, high performance anomaly detection models. All right. As we know that the real world data sets are highly imbalanced. So what do I mean by this? Yeah, there's so many normal samples when we look at the data sets that we are given by customers in industry, but few anomalous samples. If we look closer to this samples, for example, these are from Visa dataset. You might be aware. Thanks to Lafa and team, that's an amazing dataset. So yeah, so many normal examples, but few anomalous samples, and this makes it quite challenging to use the existing supervised models. If we had the chance, supervised model can perform quite high, but when we apply these models, yeah, in reality, the performance are quite low. And there is also another problem. So even though we can find a model that performs quite well using supervised models, the abnormalities are often unknown and might evolve or maybe change over time. So when we are talking with customers, they introduce their problem and they say, oh yeah, we have these anomalies, we are interested in this and that, but over time they say, oh, by the way, there's a new defect here, so we want to focus on. So it's like kind of always there's new class that we need to take into account. So what we need to do here is, as we all might be aware, is just, okay, focus on the normals, learn the normality, and then depending on what we learn, we can just find the abnormality during test time. Yeah, so for example, here we can see there's so many different, is everything all right? I'm getting close to the microphone. I might step on the cable, might be affecting I don't know. See. All right. All right. As I mentioned, there's tons of algorithms every week. If you set your Google Scholar or some other tools, you just keep bombarded by new emails saying that, oh yeah, there's a new paper coming out outperforming the state of the art. It's really hard to keep up with. And if you look at this, yeah, there's so many new papers and all competitive. As I said, it's quite hard to keep up with, right? And the problem is the reproducing these papers are hard, right? So you probably saw this meme online many times. You see, this paper is quite nice, but many of the times you just can't find the code, right? It's a bit, yeah, I mean, that happens. But when you do find the code, like the GitHub link, you just, oh wow, that's good. I can reproduce the experiments. That's nice. And if you find that it's with your favorite framework, that's even better, right? So if you're a TensorFlow fan or a Torch fan or a Lightning, whatever, and if it's written with your favorite framework, then yeah, amazing. And you just run it, and sometimes it just doesn't work, right? It's annoying, but it happens. But if it runs on your system, that's great. But if it doesn't run, yeah, we just create issues, right? Saying, oh, I just ran this, but training doesn't work, or this, I can't install it, Torch, CUDA, whatever. But yeah, you just get the response like, that works on my machine. So I don't know what's your problem, yeah, and then yeah, you know this meme, right? This is basically how we decided to, create Anomaly to make people's life easier. Yeah, that's a quick introduction. Right. Yeah, just a summary. Anomaly is a library to design, develop, and deploy deep learning models. What do I mean by this? So we don't want just, design algorithms or just get training performance, but, we're a bit more ambitious, and we want a tool that, not only just to design something, but, all the way through the machine learning cycle to deploy that model for a real-time application or real-world use case. So that's the main focus. Right. So we start with state-of-the-art anomaly detection models. So we try to implement as many models as possible, thanks to the community help as well. So they're helping us implementing those algorithms. So this is to reproduce the existing research, right? So this helps us to quickly just basically use those models that's already available out there. So this is useful for research and also for industry as well. So like if you're doing for research, you can just basically reproduce the numbers and then design a model of your own. Or if you're working for a real world problem, you just take the model off the shelf, you know, just use it. That's quite handy. We also provide a modular API for customization. It's really good for prototyping new ideas. Let's say you have an idea, but you don't want to deal with all this boilerplate code, you know, write everything from scratch. Yeah, the API gives you the opportunity to basically create new models, or maybe just new ideas, or basically just you can design your own pipeline for your real-time application as well. So both useful for research and development. Also, it provides a CLI for end-to-end machine learning lifecycle, like all the way from scratch, you know, to train or validate, test, export, deploy, whatever. Also, some other features like logging, hyperparameter optimization, benchmarking tools. And why are these useful? Basically, we can accelerate the experimentation, right? So let's say we design a pipeline, but most of the time, if you're writing a paper, we just need so many numbers, right? Just to compare with the state of the art, or how it does and stuff like that. Or if we're working in industry, we still need numbers to see if this algorithm works fine for this specific use case and so on. So we can just use these tools to accelerate this experimentation. And probably this is more for industrial use case or maybe for practitioners. But when you want to use the model for a real-time application, most of the time, what we have in the torch model or maybe the raw model is not so good for you know, to be used at the edge on an edge device, for example. So in this case, we want to optimize these models to speed up the acceleration. And we have a bunch of tools to quantize these models, like the same model without the accuracy sacrifice. Basically, we can accelerate the performance so that we can, rather than using on a big chunk of GPU, we can use the same model for maybe on a small device like this big. So yeah, that gives us the same performance basically. So that really improves the possibility to use those applications in any sort of real world application. Yeah, I mean, this is also kind of relevant to more like a real-time application for deployment. So if you want to use Torch, Lightning, OpenVINO, Onyx, or Gradio, so there are a bunch of tools that are already available there. And in terms of the domains, we're trying to support like image, depth, and video, but we're trying to get into other fields as well. But yeah, I mean, I guess this is sufficient for this workshop as the scope is visual anomaly detection. But yeah, this is all the state-of-the-art public data sets like MVTech, Visa, and other data sets are already available there. So it's just as easy as importing those data sets from Anomaly data. In terms of the tasks, we try to provide 3 different tasks like classification, detection, and segmentation, meaning that the classification one gives you a global prediction that decides if the given image is anomalous or not, or if it's for detection and segmentation, if it gives you the localized anomaly detection. But I guess in this, in a research focus, classification and segmentation is more interest in this workshop, as many papers report their performance numbers using classification and segmentation. And yeah, this is kind of a taxonomy of the papers that we already support off the shelf. This is a growing list. I think there's also a couple of papers missing here in this graph. But yeah, it's a growing list, as I said. All right, let me just go over the high level workflow. So we start with training, and basically we train an unsupervised training framework and get the train model. But nowadays this is also optional because, you know, we now have zero-shot models as well. So for example, yeah, it probably just doesn't need a training. We can just use the zero-shot models off the shelf, and there's already a model available in Anomaly. It's a wing clip paper from last year's CVPR from the Amazon team. So it's there. So if you want to try it out, yeah, it just gives quite nice performance, even though you don't can train anything. Anyway, so after training, if we train the model, we have this validation and test, and we have this adaptive thresholding mechanism, which is a crucial step in anomaly detection, as many of you are aware. And then we have some thresholding mechanisms built already. It's either adaptive or manual thresholding is available. And based on this threshold selection, we compute the matrix using all these anomaly detection evaluation matrix like PRO, AUROC, or AUPMO, or you name it. And then this next step is the optimization part, which is optional, but as I mentioned previously, it is for those who would like to basically use the model in a real-time application. It's from FP32 or to FP16 or int8. It's just to quantize the model to have a better inference, or maybe faster inference. And then finally, we can just use these models for a deployment part. So that's the high-level workflow. Maybe I can also talk about the high-level architecture. So we have both CLI and API options, and this is mainly for to make it possible for everyone, because I see that some people like to use API, get their hands a little bit dirtier with the code base. So the API is a good choice for them. But if they would like to use some users just want to use the CLI off the shelf, have a configuration file, pass it from the command line, and then get the job done. That's also possible. And how it's done is basically there are a few components to use. The engine is one of them here. And the engine, if you are familiar with PyTorch Lightning, under the hood, we're also adopting PyTorch Lightning mechanism, but we have this engine to orchestrate everything. And then we pass data models, callbacks, matrix, and visualizers, basically all what you need to train and test the pipeline. And we pass all these components to engine, and the engine orchestrates all these entry points, all the way from training to prediction, including hyperparameter optimization and benchmark as well. Right. I think there's a duplicated slide here. Right. I think so far I talked about how we can, utilize these tools, and how the high-level overview and high-level architecture is. And I can quickly talk about the installation, because my main point at the beginning of this talk was the reproducibility, and right. So it should ideally be easy to install in the first place, right? So when you do pip install Anomaly, basically you can have all the stuff that you need. And when we look at the installation options, it gives you a hardware agnostic and configurable installation. For example, when you install Torch, you see that sometimes the pip installs the wrong version of the Torch, maybe missing CUDA or CPU version and things like that, and then you just need to go back and manually install the Torch. So basically, we try to sort this out for you, and then the CLI command will check your system if you have the GPU or if you have the CPU and so on. So it kind of makes the life a little bit easy for the user. Right. So let me quickly talk about the entry points. Right. So the training. It's as I mentioned, we have both API and the CLI version of the training. If we talk about the API version, it basically gives you all the freedom if you want to code and dive deeper into the details. So let's say you want to train a patch core model. Again. Can you hear me okay? Oh, okay, no, much better. I can hear myself. So, yeah, so if you want to basically train a patch core model on MVTech data, what you just need to do is import the MVTech data set from the data and the patch core model from models. Of course, you need the engine to orchestrate, but that's basically what you need. And initialize these components, and then just call the engine.train, pass the data module and the model into the engine, and that's it. So you can have what you want. So it's like few lines of code, and you can basically get the patch core model, or yeah, if you're interested in other models like Efficient AD or PADM, or maybe whatever the model you're interested, also it should be available in Anomaly or be supported. Yeah, this is basically 7 lines of code is what you need, and you'll get all the training and testing and export functionality. But as I said, if you're interested in the CLI, you're saying that I don't want to code, I just need some run the experiments and get the results. Basically, you just need to call the train subcommand and pass the data and the model, and that's it. So it will train a model for you. Let's say you don't want to use the default values, but you want to override some of the arguments to customize your training. So you can do that as well. This is just a simple example. I want to change the category, but if you want to change the model parameters or the data arguments, you can still do like by passing model dot whatever parameter you want to change. Yeah, it'll be available there, and it'll train the model for you. And it's important to note here, I think, is that this API and the CLI gives you one-to-one parity. It's not like, CLI does something else and the API does something else. It's basically whichever approach you choose, you get to the one-to-one parity. So you'll always get the same results. So I think that's kind of the important bit. All right, so let's talk about the test and export. So let's say you train the model, you have a trained model with the proper weights. What you need to do is basically test the model to get the performance, right? So yeah, it's same as last time. What you just need is call the test entry point, pass the data module in the model, and you'll get the performance basically. If you want to do it from the CLI, it's the same approach. You just run the test subcommand and pass the model, pass the data, and you'll just get the results. And if you're happy with all the performance, what you need, and you would like to use it on the edge or for a real-time application, you can just export the model via engine.export. And as I mentioned, there are a couple of options to choose. If you want just raw torch, you can choose the export type as torch, or if you want Onyx or OpenVINO to accelerate the performance on on CPU, more specifically on Intel hardware, for example, on a small device. Yeah, there are a bunch of options, and then you export the model, get the exporter model to use for inference. So it's all available, and again, one-to-one parity for API and CLI. I think that's the nice bit. Right. For another entry point is the benchmark, which I think it's quite important for both research and development purposes. So okay, so this is the wrong one, but anyway. So what benchmark is doing is basically, let's say you want to run some experiments and, run multiple models, multiple data set categories to basically get a lot of numbers to store. Benchmark will give you the option to do so. So this means that if you're writing a paper, you can easily produce those numbers or reproduce some of the existing models, or just fill out the table that you're writing the paper. So the benchmark will give you what you need, and I'm going to talk about that shortly. Now I'm going to shift my focus a little bit onto the modules that we have, because previously I talked more about the entry points in the main workflow, like training, testing, export, and stuff. But now I'm going to talk about the data modules specifically, and start with the data modules. So these modules are kind of the building components that you can basically use, even though you don't use the entire pipeline on its own, but you can just take out one of these modules, like data modules, for example, and use it for your own project or for your own research. For example, for the public benchmark support, what we can do is, let's say you want to use MVTech or Visa or BeanTech. You just import it from anomaly.data and use it for your own project. And what this does is basically this data module creates all you need, including the train data loader, validation data loader, test data loader. So you don't need to specify anything like, if you're a Torch user, you need to manually create all these train data loaders, validation data loaders, and all that stuff. So this data module does everything for you, and stores in one object. So it's really easy to access to those data loaders and many other attributes as well. So for example, if you want to access a batch, what you just need is just go through the data module.train data loader, and it will give you what you want. So the image path to the original image if you want, and the image tensor and the label tensor. So like everything is ready so that you can use it to start training your model, or doing the initial step basically. Yeah, so this is just an example. If you just look at the shape, for example, the batch size of 32 and 256, but you can customize this. So it's so many options there. And this is same for the validation and test data loader. But when we first introduced this, we received a lot of questions. I think I should just come closer a little bit. Yeah, we received a lot of questions from the community saying that, hey, can I do that for a custom data set on my own, my own data, custom data, whatever. This may not be so well suited to a research, maybe just for publishing papers, but it has a significant use case in industry. So a lot of people just use custom data, right, for their specific use case. In this case, we provide a folder data module with all the customization opportunities, all the way from the different task types like classification, if you want to do segmentation, and so on. So if you do segmentation, you can provide the masks. If you don't provide the mask, it'll just do it like a classification, all different sorts of customization. And then we noticed that this is used by many people, especially for their specific use cases. And again, the rest of the stuff is exactly the same. The data module has all these train data loader, validation data loader, predict data loader, like for every data loader that you need. And it gives you the right tensor and the label and so on. Let me just quickly go over the model API. So again, this is also another unit that you can just take out and use on your own. So let's say you want to use PatchCore or Efficient AD or PATM, whatever. It's available already, so you can just import it from Anomaly models and instantiate the model with your arguments that you want. For example, here I just choose the default arguments for PatchCore. Latha can correct me because that's their paper. But yeah, basically the default arguments for PatchCore, and we initialize the PatchCore model. And then basically when you forward pass the train data from the previous slide that we have from the data module, and we can get the predictions. So, no boilerplate code. Everything is quite high level. But I think the most important thing here is the custom model. So because, there are a bunch of models available in Anomaly already, but one might think that, okay, how can I use this thing if the model that I'm interested in is not there? So in this case, we also made available like the custom model integration. So if you want to integrate your own model so that you can utilize all the features of Anomaly with your own model, you can do that. And this also helps us to, you know, increase the number of algorithms available in Anomaly, because as I mentioned in the beginning of the talk, there's so many papers now, and we can't just keep up with adding all these algorithms on our own. So we need the community help. And with this custom model integration, so that's possible. So first thing first, the custom model API, we need a torch model and the anomaly model. So the two, we wanted to separate these two things. So the torch model here on the left is what it does is basically it performs a forward pass. So like when you have the image and the, you know, the model, what is the behavior, or what should be the implementation like, you know, when you forward pass this model, and what will your output will be like, you know, that's basic forward pass mechanism. And we do that within the torch model definition. We also have this anomaly model definition. So that's kind of defines the workflow. So for example, we inherit this anomaly module, and we have this model, let's say autoencoder. So as you know, the autoencoder is like one of the quite well-known anomaly detection models for quite a while. So let's say this autoencoder model, we pass this image and get the autoencoder output, like the reconstructed image. We can just define this torch model here, self.model, and the self.loss. So whatever loss you want to use, in this case is SSIM loss, but you know, it could be anything basically. What anomaly module does is it basically utilizes the lightning under the hood, but organizes everything for you. And then again, no boilerplate code. So you just configure your optimizer if you have an optimizer, and you have your training step. So whatever the training step is, let's say in this case, you just pass the model, forward pass, get the reconstruction, and then pass it to the loss and get the loss and return the loss. And whatever the validation step is, like, you know, whatever you want to do in the validation step, you can define it here. And similarly, like you can also define, let's say you have some specific behavior that you want to do in your predict step or test step. So you can define it here. But with this basic setup, we can quickly integrate this autoencoder model into Anomaly and use all the Anomaly features, you know, data modules, HPO, benchmark, and, you know, all these functionalities you can basically use. In fact, we wrote a blog post for PyTorch. My colleague Dick down there, he wrote an amazing blog post doing this implementation with this simple autoencoder implementation. I think, correct me if I'm wrong, Dick, but it was almost 88% performance on MVTech, so which was quite nice. And with like few lines of code, it just managed to get like 80 plus or close to 90% performance. So you don't need to do any, you know, boilerplate code, write torch, all these, you know, low-level torch details if you follow this approach. And I find it quite handy, and hope you can find it quite handy as well. If you don't like some of these features, just create an issue or some, you know, feature request. We'll try to sort it out. Right. We also provide some custom model components as well. What do I mean by this? So, you know, in anomaly detection, and many times we just use some maybe more conventional machine learning approach like PCA or multivariate Gaussian or mixture of Gaussian or whatever. So like if you look at the state-of-the-art models, many of them sometimes use these models. One might just say, okay, you know, these are already available in scikit-learn. I can just import it from scikit-learn. But the problem is that those are written in NumPy, even though they are optimized. What the problem is, when we work with this pipeline, you have the torch model and then pass it to a scikit-learn's PCA or multivariate Gaussian or any other machine learning component. It moves the GPU tensor to CPU, convert it to NumPy, you know, the conduct, you know, carry out the operations, whatever the PCA or maybe other like other algorithm you're interested. And then output is from NumPy to tensor, and then from CPU to GPU. And overall, when you want to use this for an industrial application, this caused quite some trouble in terms of the computation. So what we do here instead is we port all these implementations from scikit-learn to here in Anomaly and write everything in Torch so that we can have like end-to-end model pipeline written in pure Torch so that these algorithms also can be run on GPU. So we find it useful and many observe that this also increases the computation in a positive way. Yeah, so an example, like let's say I have a custom model. Basically, I can just import PCA or multivariate Gaussian and use these components within the model pipeline. So again, the nice bit is that this becomes an end-to-end Torch pipeline. No NumPy, no other libraries. It's just pure Torch. Yeah, also the matrix, maybe I can just quickly talk about that. Yeah, in anomaly detection, we tend to use AU-RRC or AU Pro. Recently, there are new evaluation matrix being introduced as well. But we try to combine all these matrix implementations in one place as well. So you can do anomaly.matrix. You have all these anomaly detection matrix as well. So everything in one place. So let's say you want to use F1 score, AU-RRC, AU Pro, AU PMO, or whatever. You just pass these matrix to engine, and the engine, when we train the model, basically we will get all the matrix. Another important feature I think might be useful for the research community is the logging. So let's say you just perform loads of experiments. Some people just prefer to store the output in a CSV file and put in an Excel sheet or just process the CSV files. But these days we have loads of amazing experiment management tools out there like Comet, Weights and Biases, TensorBoard, Neptune, you name it. We support all these stuff basically, but more specifically on a couple of them. So basically just need to import the logger of your choice from anomaly.loggers and pass the logger to the engine. And the engine will make sure that, whatever you train and whatever you get is also logged into the experiment management tool of your choice. So that's quite handy for research use case. So you have all these numbers, all these, artifacts logged into these tools. Yeah, so here's an example. We just run the, MVTech and log it to Comet and TensorBoard at the same time. So yeah, maybe it's good to mention that as well. So let's say you want to log these into multiple loggers, not just one. So just pass it to Comet and TensorBoard at the same time. So you can have access to all these experiments. So this might become handy when you write papers or, carry out your research and, would like to have access to all these artifacts and numbers. So you have everything in one place. Finally, the benchmarking stuff that I was trying to show earlier. Yeah, so the benchmarking is also another important feature that would be quite useful for research community, also practitioners as well, to produce loads of numbers to compare, basically. What we need here is just a configuration file. We specify that, you want, this is just an example, but you can just configure it however you want. So let's say I want to run the CUDA and CPU to see the performance of these models on both CUDA or GPU or CPU, basically. Let's say I want to run multiple models, let's say PatchCore and Efficient AD, or maybe more models. You just specify it here. You want to run MVTech and all the categories, produce the table. Yeah, just specify the categories here. The image size, let's say you want to observe how the model performs on different image size. You can pass different image sizes here. And all these different sorts of arguments that you would like to see the performance, it's possible. And basically pass this configuration file to the CLI via this benchmark subcommand. And that's it. So it'll just run everything for you, and you'll have all these files available. And yeah, this is kind of a diagram showing how it works. So this benchmark job is basically, this is your job. And we have a benchmark job generator that generates all this stuff. And we would like to run it in parallel if possible. Let's say, you have the compute power. So you don't need to deal with all these parallel running and all that stuff. Basically, just pass this configuration file and Anomaly will handle all these stuff running in parallel if possible, and then get the performance numbers as quickly as possible. So this is just an example how benchmarking is working in Anomaly, but also we noticed that we could utilize this one for many other stuff, basically custom pipelines. So like the chain tasks that you would like to do. Let's say you have a model, you have another model, you want to stack them together, for example. So that's possible. Like you want to do, for example, ensemble model, for example. So you could utilize this custom pipelines. So how it's done, basically here, we again define a job. We have a runner for this job. It just runs that job. And we have, let's say, another job. So this could be another model, or maybe another components that you would like to run. And then we can just control this, either in parallel or in serial. For example, this is just a dummy example, but let's say I have an experiment. I would like to run some parts in parallel to speed up the experimentation. But in some cases, there might be some use cases that, you run them parallel, and then at the end, you want to carry out some operations in series, like one to the other. And in this case, you might need the serial runner. So it is possible to stack them together, like run the parallel stuff together, speed up the experimentation, and then do the serial operations, and then finally combine all these results together. So that's also possible. It's completely up to your imagination or your use case, whatever you need. So the custom pipeline will enable whatever you need, basically. Right. So with all these functionalities, basically we can perform an anomaly detection use case, like the example that I show at the beginning. Thanks to Paula sitting right here, she just created this demo. I think she spent like a couple of minutes to train this model, either Pattern or PatchCore, like just a couple of minutes, and the deployment was kind of there. I think it's amazing to see that, with a couple of minutes of training and, optimization to run on an edge device, to integrate that into a system. Yeah, it kind of shows the use case all the way from, the data collection, training, validation, optimization, and the export and deployment. So with this pipeline, this seems to be possible. I think I can stop here. It's 40 minutes already. This is the team. We are a team of 4 with many other contributors around the globe. But yeah, for the V1, basically, this is the team working on the project. Two of these folks are here in the room if you would like to chat. So I think they will be happy to chat about the project itself, or the feature request, or the things that you want to see, or maybe anything you want to discuss. We'll be here all day, all week. So happy to discuss. Yeah, if you would like to contribute, or as I said, create issues, complain about something, yeah, these are the QR code if you're interested. As I mentioned, we have so many contributors, apart from these 4 and maybe a couple of other colleagues, including Paula. Yeah, we have 85 contributors so far across the globe. So yeah, we are quite happy with this number. And I see some familiar faces contributing to Anomaly as well. That's amazing to see. Yeah, I guess that's about it. Thank you very much.
Okay, if we have any questions for Samit, then you can just come up to the microphone here, and we can take it from there. Over to you.
Hi, thanks for your talk. Congratulations. Let's say I have I publish a new data set, a new anomaly detection data set, a new anomaly detection model. what are the requirements to integrate them into the Anomaly? If there are any requirements, let's say it has to be popular, I don't know.
No.
Okay.
It's I mean, as I said, we welcome any contributions.
Okay.
There's just a guideline to integrate a new data sets. Basically, as long as you inherit the base anomaly data module and then integrate whatever you have for any, like for MPTech visa, all this stuff, we follow exactly the same procedure by following the anomaly data module interface. It's pretty much the same. So people just, a lot of contributors just say, you know, I have this paper. Can I just add it into Anomaly? And we say, yes, yeah, by all means. We try to say, we never say no. So you're more than welcome if you have a data set. If you have a data set, I'm happy to talk about the details as well.
Actually, I do have a data set.
Okay, that's good. Yeah.
Yeah, but yeah, so my question was in the sense that so someone that can import Anomaly and install, so someone could import this data set of mine, for example, like they import MVTech or any other, right? Okay.
Yeah, that's as long as you follow the, you know, the interface, the Anomaly data module interface, and then create a PR. That's pretty much it, basically. If you have any license constraints, that might be the only problem we might need to discuss. But other than that, yeah, it's possible. Just you can create a PR and then we'll just review it and merge it.
Thanks.
Thank you for this great presentation. Great tool, by the way. My favorite part is the folder feature. Great feature, because coming from academic and going to industry now, there's a gap. So I appreciate that feature. Definitely great feature. My question is, when we use, let's say I want to use the folder feature, is there a specific requirement for the folder structures, the images in that folder to be able to train my own models and like kind of use that custom feature?
Well, it depends on the model in a sense. Like, let's say if your images are 32 by 32, you know, and then if you're training a model with a transformer backbone that reads like 400 by 400, for example, that might be a problem. I might need to double check if you have some checks to ensure that that works fine. But other than those constraints, yeah, if you just pass the images to the folder, like, you know, if you have a folder structure, we try to make it as configurable as possible, so that you can customize it however you want. But as I said, apart from the model constraints, I don't see any problem with customizing the folder itself.
Okay. What about if you have like a nested structure of folders? Because that's also another application in industry where like you have a nested structure.
Yeah.
Would that also work with the folder tool?
I think it would work because we're just globe and do like a recursive reading.
Okay.
But the only problem would be that it may not give you the type of the anomaly and label, but we're working on it. So there are recently, especially this year, there were a couple of papers doing, you know, the type of the anomaly classification as well. So that's kind of on our roadmap. So rather than just focusing on anomaly versus the normal, we want to also focus on normal versus what type of anomaly is this. So in this case, your nested folder structure, yeah, might be handy, but currently it's just reads it as all anomalous, basically.
Right. Thank you very much.
Sure.
Hi, I'm Marco Cristani from University of Verona. Thanks. I think it's a huge contribution. So are there any requirements in order to get accepted to be part of the code? Maybe there are some contributions that are not high quality, so maybe.
I think the only requirement is that you create a pull request. As long as our tests pass on the CI, then and our reviewers happy with the code, and that's fine. Of course, we have to be a bit like, you know, careful with the code quality and stuff to ensure that it's always the highest quality of code. So we set up some tests in on our CI to ensure that stuff. But once the tests are passing, we just merge the code. And when we review the code from contributors, we're trying to help as much as we can so that, you know, those tests, you know, might be not familiar to those contributors, but we know them already. So we just try to sort out and help the contributors. But yeah, as long as you just create a PR, and
Okay.
we'll try to help as much as we can.
So there is no need to be on top of the list or some.
No,
Okay.
not at all.
Okay.
Yeah,
Thanks a lot.
you're just more than welcome. Anyone can
Okay,
contribute.
thank you.
Hi, thank you very much for this great presentation and great tool. Could you explain more about model optimization, please? Like, my knowledge about this topic is quite limited. I only know I only think about ResNet, like quantization of ResNet like backbone, but yeah, so could you please explain more?
Yeah, this is a great question. I think this might be a bit out of scope of this talk though, because we have an entire day tomorrow talking about this stuff as a tutorial. And I see one of my colleagues, he's an expert in this quantization back in the room. So he can explain that to you much better than I do. He's a principal engineer at Intel, more specialized in quantization stuff. But it's basically, yeah, maybe if you talk to him, he'll just outline everything to you. Or if you're more interested in details, you can join the OpenVINO talk tomorrow. Like there's going to be 2 hours, maybe more than that, a session going over all these quantization stuff. Because if I just go into the details here, probably I'll just steal quite some time.
Okay, thank you. What is the name of the tutorial?
Talk to Paula. She's there. Yeah, she's gonna give you the details.
Okay, thank you.
Hi, so
Hi.
very nice job. So earlier you were talking about the code quality, but I was wondering if you noticed, or actually what's your policy on discrepancy with the results published by the papers that present those methods? Did you notice any major change? And in that case, what do you do? Do you just accept it, or do you contact them and try to work it out?
When you say when we implement the models, we see performance discrepancy with the reported.
Yeah.
Yes, that's kind of a problem.
Yeah.
Sometimes it happens we try to follow the exact same approach published in the paper, and yeah, there's some results different. This could be due to many reasons. Yeah, we can discuss this offline. Sometimes we try to contact the authors to, you know, to ask them clarify, you know, why there's this discrepancy. Would it be because, you know, there's something that is not mentioned in the paper, but in the code base, or, you know, some cherry picking, or, you know, something else? Yeah, that sometimes happens, unfortunately. Yeah, and then that's the worst part of the implementation bit. Yeah, I agree.
Yeah, okay, thanks.
Thank you very much. I think now, in the interest of time, we're going to move on. But if we want to thank Samit again, that'd be great. Thank you.
All right. Then next up we have Shai Abidan. He's a professor at the Tel Aviv University. He received his PhD from the Hebrew University of Jerusalem, and he's very established, published a lot of papers in various areas of computer vision, like object tracking and 3D object detection, and also has a lot of industry experience, been working at Adobe, Microsoft Research, for example, just to name a few. And also appreciate his flexibility, because we had to shift some stuff around schedule-wise. So thanks for that. And I'm very excited about his talk in particular, because the title of his talk is Everything But Anomaly Detection. So it seems to be a perfect fit for this workshop. And thank you very much for being here today.
Just a short information, some of you may have noticed we are running like 20 minutes behind, but since the talk was cancelled, we will then in the end still be in time for the lunch break. So we just have the coffee break after the keynote and then continue as planned.
Okay, hi. Hi, you hear me? Great, good morning, and thank you for coming. So this talk is everything about anomaly detection. Hopefully this will be the outlier of this workshop. And this is the only slide I have on anomaly detection. Really it is. So you have a distribution of people's height, and you're given a query point. And is it anomalous or not? Well, you define a threshold, and if it's below a threshold, then it's anomaly, and if it's not, then it's not. And that's all I have to say about anomaly detection. Which begs the question, why all of you are here? Because all of you know Gaussian distribution, right? We can make it interactive and ask what you think is the goal of visual anomaly detection, or I can give you straight the answer that I came up with when preparing the talk. So this is the answer I came up with. Anomaly with respect to what? And that's a crucial question that people gloss over quite often. They rush to the implementation, they download the latest model, but they don't often stop and think, what is the representation that best fits the problem that they want to solve? And I'll show you examples later on of what I mean by that. So if you took a computer vision course anywhere in the last 10, 15 years, you probably saw this slide. There are many facets, many features that you can look at an image and try to detect anomaly detection with respect to it, right? But if you have a concrete problem, then think long and hard about the representation that best fits the problem that you want to solve. Okay? So let's dive right in. Without knowing it, I did a couple of anomaly detection projects in the last few years, and I want to share the insights, the lessons I've learned from doing them. And before starting, this is a paper that was published by Yedid Hoshen and his students a couple of years ago. And essentially, it did what I just said. It says representation is all you need. That's my reinterpretation of the work he did. Instead of working with pixel values, just do deep features. So if you have some training set, you embed them into some deep feature space, then you measure the average distance to your nearest neighbor. That's essentially equivalent to looking at a low distribution, regions with low distribution, low probability in your distribution, and that will define the anomaly in the data, right? And he got state-of-the-art results back in the day. And that's the only thing he did. It's like a minor thing, but that's what made the system work. And I'll show you how it applies in other scenarios as well. One of the problems I, as a reviewer, often have is that when you're doing this type of experiments, you use very unrealistic data sets like C410 or something like that. And moreover, the way you run the experiment is, in my opinion, the wrong way, in the sense that you define each class to be the normal and the remaining 9 classes to be the abnormal. And that's not how the data in the world behave. I'm sure the community moved past it, but this is something that always bothered me, so I thought I'll mention it. Okay. So I did a couple of projects on video anomaly detection. And the standard data set in this field is the Shanghai Tech data set. And what you have here are snapshots from some of the videos. And the normal behavior is people walking, and the abnormal behavior is people cycling, jumping, and such. And let me show you a couple of, examples just so you familiarize yourself with what's going on here. So what you see on top is the video, and on top of it, you see the pose, the human pose that we estimate. And what you see at the bottom is the negative, it's the log likelihood of the probability of an abnormal behavior. And the red region is the ground truth, and the curve you see is the result that we obtain. So right off the bat, you see that the major decision that we made is to use pose graph instead of raw pixel values. And as you'll see, it has a lot of impact on the results that we get and the things that we gain from this. And the way the test is designed is that it's enough for one person to do an abnormal activity for the entire frame to be flagged as an abnormal example, okay? And let me skip. So a bicycle rider is considered anomalous. And there is another data set that's the UB normal, which is a synthetic data set, and you can train your system on that and measure performance as well. I'll show you just one example here. Okay, so someone's running, behaving strangely, that's anomaly. So the first question is, why use PostGraph? And the reason you do it is going back to the question I asked earlier. What is the goal? And the goal that we decided is the goal of our anomaly detection is motion. And motion is best captured by a PostGraph. You don't care about the appearance, you don't care about lighting, you don't care about camera pose and angle, you don't care about the background. All these are nuisance parameters. So instead of forcing your method or your algorithm to somehow learn this, simply throw them away from the get-go and focus on the thing that you really care about and try to solve that, okay? And once you start working with industry, other constraints come into considerations. For example, fairness. If you're talking about anomaly detection in video, it's usually, it might be used in surveillance applications, right? And then the question of fairness comes into play. It's not often discussed, maybe in the realm of anomaly detection, but every computer vision researcher should think about this aspect. So here is an example. There are two images here. Can you infer which one is of a man and which one is of a woman? Young or old? Ethnicity? All these parameters are irrelevant when you want to do anomaly detection with respect to motion, right? And so you throw away all this stuff and you gain additional credibility within the industry itself. So in this particular example, it's a girl playing soccer and a man doing meditation, right? And you've gained this almost for free by choosing the right representation. So this is the paper we published a couple of years ago. I'll briefly go through the steps. You can read all the details in the paper. The code is available online. But just to drive home a point. So you start with the video on the left, and then you run your favorite pose estimation algorithm. You get a space-time graph. And then you run an encoder. You get a latent vector representation. And then you cluster the samples in this latent space, and you do soft assignment probability. You end up with this thing here. And you assign a normality score to this thing. You use Dirichlet processes to do that. The details are not relevant here. But if you take a step back and look at what we did here without realizing it at the time, it's all a matter of representation, right? So the original representation is pixel. And then we transform it to a space-time graph. And then we embed it in a latent space vector. And then we did clustering and assign it to a soft assignment vector. And then we measure the likelihood of the example in this space. So it was a very long and difficult process, but that's all we did. And the results were state of the art at the time on the Shanghai data set, and you can see them here. This is not what I want to focus on. Another issue that I always find important is how to measure results. So usually you have this table like so, and you report the best results, but there are many different nuances that I think are very relevant, and especially if you're coming from industry and also in academia, you should pay attention to. We did this odd experiment called coarse grain anomaly detection. And we tested the algorithm I've shown you in the previous slide on two other data sets called the NTU RGB dataset and the Kinetics 250 dataset, which is a subset of the standard Kinetics dataset. And what we did here is instead of having one class normal versus the other abnormal, we've tried two splits. One is few versus many, and the other is many versus few. So in few versus many, if you have 60 classes, for instance, you pick 5 classes as normal and the rest is abnormal, and then you flip. You have 55 as normal and 5 as abnormal. And this really drives home the robustness and the power of your algorithm. And we also have two sets of random versus meaningful. So in random, you randomly pick 5 different behaviors and cluster them as normal versus 55 that are considered abnormal, and vice versa. And really the results, you should look here at the bottom, and we show that the algorithm is pretty robust to all this variation. And you have here 5 versus 55 in the NTU data set, and 5 versus 245 in the kinetics 250. And you have the flip as well. So you have 245 normal behaviors versus 5 abnormal behaviors. And that's a very, very important, powerful tool. It gives you a lot of confidence that the algorithm you developed is really robust and generalizable and useful for different scenarios. So as I said before, all we did in this work is change representation, starting with the pixel values and ending up with this soft assignment probability on the right that gives you an anomaly score. But going back to the first slide, what we really want to do is map the data to a Gaussian, right? That's all anomaly detection is. And luckily, there is a tool for that called real NVP, or normalizing flow. And what normalizing flow does, it learns a bijective function that maps you from the input data X to some latent space Z. And because it's a bijective, it allows you to learn a Gaussian in the latent space, right? So during training, it fits a Gaussian to the data in latent space. And during testing, you take your sample, your query, you map it to this latent space. You already have your Gaussian in this latent space. You can measure the likelihood, and that's the normality score that you want. So the entire cumbersome process that I've shown you on the first slide, on the top part, is simplified to a single algorithm normalizing flows that takes data, maps it to a Gaussian, and we're back to square one. We solve the problem, right? And I skipped the details. Or the student who did the project had to do some fiddling in order to fit normalizing flows to work with graph data, but that's not the key issue here. But there are several benefits that you gain by doing it. So the size of the network is 1,000 parameter. This is not a typo. Training time is less than 15 minutes. Okay, so it's extremely fast to train and work with. And of course, I'm cheating here because we're riding on top of pose estimation algorithms that might take more compute power, but that's great because as the more they will improve and get better, the better the input for our algorithm will be, and the easier it will be for us. And since most anomaly detection on video use pose estimation already, why not take advantage of that and use it? And because the network is so small, runtime is extremely high. We run at almost 200 frames per second. Okay. And normalizing flow is not a silver bullet that solves all problems. If you increase the number of parameters to many thousands, then it might fail and not work properly. But we found that this postgraph data is really the sweet spot in terms of giving semantic information and being very compact. And the nice thing is that we can generalize it to other domains. So I'm currently doing a project with biologists on fish data, the behavior of fish. So as far as I'm concerned, men and fish are the same. They're just postgraph data that you need to analyze. And we have other projects in the pipeline that take advantage of this thing. Questions? Okay, I'll skip the technical details. You can find them in the paper. I'll just show that you get state-of-the-art result. The paper was published in ICCV last year. You get state-of-the-art results, as can be seen here, by using this postgraph data. You also get state-of-the-art results on the UB normal dataset, which is a new dataset that was published. And again, because it's a good representation to work with, you can do nice ablation studies. For example, you train on one and test on the other. And because the representation is about what you care about, it's about the pose, then you can train on Shanghai Tech, test on UB normal, and get almost state-of-the-art results, just out of the box. Of course, you can train on both of them, and this gives you a kind of natural space in which to work, train, and test on. Okay? And another thing that I think is really important that should be done is trying to mimic real-world scenarios where you introduce noise in your training data. So the assumption that your training data is clean is not always valid. And one way to do it is by infusing noise into the process and measuring the performance of the algorithm. And that is what you see here for both the Shanghai Tech and the UB normal data sets. The x-axis is the amount of noisy data that we inject into the training process. So these are abnormal examples that we purposefully added to the training data. And you see the degradation is quite graceful, meaning the algorithm is robust to this type of data infusion. Okay. So these are past projects. Let me skip ahead to a project that we're currently doing. If I can, is there a way to? So this is an aerial imagery data set called DOTA V2O, and it consists of 11,000 images, aerial images from different sources. And it is annotated with 18 categories with 1.8 million bounding boxes. Okay, and here is a zoom in of the type of data that you see. You have ships and bridges and small vehicles and large vehicles and soccer ball field and so on and so forth. And at the bottom, you see here the distribution of objects of different size. Here is the number of pixels per object, and this is the orientation. So we made some simplifying of assumptions, but this is a large-scale real problem, okay? And here is the question that we were asked to solve. Is there a way to remove this? Oh. Okay, success. So the problem that we are trying to solve is, we call it novel class discovery. And the setting is as follows. You're given a classifier that can detect small vehicles, large vehicles, and the background. And the question is, given a new aerial image, are there objects from new classes? And this is an extremely vague question, right? So how do you differentiate between a novel class, a novel object class, and some artifact of the background? But this is the question that we were asked, and the question is how to solve it. And we found a way to project it into anomaly detection out of distribution type of problem. But this is the question that we were asked, and observe that we moved from a very localized problem of research in the sense of trying to solve a purely defined mathematical question into something more general, a system larger than a single component. And the way we try to solve it is as follows. We start with all the data. To give you a rough estimate, assuming we know the rough size of the object, we have about 100 million instances in those images. And out of these 100 million instances, patches, we need to find out the novel objects, if there are any in the images. So what we do is we start with all the data. We run an anomaly detection algorithm that I'll describe in a minute. And this drops us to about 10 million patches that we need to work with. And then we use these 10 million patches, we pass them through the classifier that we have access to reduce it to about 1 million. And then we declare success, okay? And it's a good question of, is 1 million samples a success or not? And I'll show you what we think and how to interpret the results. Okay, so this is the pipeline. We have a two-stage solution in the sense that you start with all the data. You try to clean it up as much as you can using anomaly detection. Whatever is left, you pass it through an out-of-distribution algorithm, and whatever is left are the new class objects that you're looking for. So how do we do anomaly detection? We rely on what is now, I think, known in the industry. We use deep features, the Dino VAT representation. And what other groups before found is that the self-attention layer of the class token is very informative. So you see the heat map from the saliency map of one of the attention layers of the network and compare it to the ground truth, and you see that the important region lights up. And if you take advantage of this representation, you simply run a non-maxima suppression where you detect patches with the highest likelihood, with the highest score, do some non-maxima suppression, and what you see on the left are the proposals, and what you see on the right are the ground truth. So this step of anomaly detection drops the number of patches from about 100 million to 10 million, okay? And the next step is how to use that information in order to, with the classifier in order to reduce it further. So in order to do that, we're using Odin, which is a very old and hopefully still old and hello? Sorry. So we're using Odin, and in one slide, what Odin does is the following. Given a sample X, and here you see a two-dimensional sample X, you perturb X and you measure the change in the softmax value. So you have some X, and this is its value. And if you perturb it, the softmax value goes up, and you measure the change in the softmax value. So if the change is large, then this is an in-distribution sample, and if the change is small, then this is an out-of-distribution sample. Okay, that's the work. That's the way Odin works. And in our setting, if the change in softmax is large, then it's a in-distribution class. It's small vehicle, large vehicle, or background. And if the change is small, then it's one of the other classes. Okay. And this is just visually showing the results that you get. And you see that it does a good job of separating background from the new object classes. On the right, you see in distribution. So these are background samples. It keeps seeing the same stuff over and over again. So it knows that this is in distribution. On the left, you see the out of distribution. These are the strange things that it doesn't quite know how to represent using the data that it observed. And we can use that to get the final result that we were hoping for. And this is the result that you get. We get a roughly area under curve of 0.94. And you see the confusion matrix on the left. So you correctly classify about 13 million background patches. You're left with about 1.6 million patches that are misclassified. And so now put yourself the hat of an industry customer. You give him this result. What is it to make of this? We declare success, right? We're researchers, 90%, that's fine. Let's go home and celebrate. But this is not really useful. So one of the things that we try to convince the customer in this case is that we are focusing on the wrong question. And that goes back to the topic I started with. What is it that you're trying to solve? We're trying to solve the problem of finding a needle in a haystack, right? So you're given 100 million patches, find the patch that corresponds to an object from a new class. But this is not really the question. The question is there a needle in the haystack? And that's a different question. And it might require a different solution. And luckily, the solution we came up with builds on top of what we did so far. So what we show here is a graph that shows you the rank of the out-of-distribution samples that we take from the ground truth with respect to the entire set of Odin scores for all the samples, the 1.6 million patches that we have. And what you see here is that the measure that you want to look at is time to first. So if you take all the 1.6 or all the 13 million or all the 100 million samples, compute their Odin score, sorting from the smallest to the largest, and then put a human operator going all the samples one by one, how long will it take him or her to find the first example from an object class that was not for the classifier, okay? And here are the results. So if you train your classifier only on small and large vehicles and background, you need to look at only 51 examples until you detect a ship. So that's the entire effort you have to put into. You started with 100 million patches. Through the pipeline, you reduced it to about 1 million. And then the human operator needs to go through 51 examples to detect, there is a ship in the data set. There might be 10 ships, there might be 100 ships, I don't know. But once I find the first one, I can designate a team to work on it. I can use this example to adjust the representation in order to find it, and so on and so forth. And if I look for a storage tank that looks even more different than a ship to a vehicle, then I need to go over 1,000 examples. And if I have a swimming pool, which is even further from the original presentation, I need to go through 5,000. And the most different thing is the harbor that is 25,000 patches away. Okay, so now I have an entire pipeline. I have a concrete way to operate and work on the data in order to get the answer that I was looking for. So I think that there is an interesting question of how do you do anomaly existence, not anomaly detection. And is there one of the things that we're currently trying to do is formalize it mathematically. Can you come up with equation? Can you come up with an analytical expression that will let you quickly come up to the conclusion that you have or you don't have these anomalies in your data? And then you decide to spend time to do the detection itself. Okay, so I'm cheating. These are not the take-home messages because I have some more, but whatever. The first thing is really representation. Every project that you're doing, you need to start with asking yourself, what is the problem that you're trying to solve and what is the best representation? And the fact that you have excellent tools and the community is providing you with wonderful libraries to do that does not mean that these are the best tools for the problem that you're currently working on. The second thing I think that is very important, anomaly detection is relevant really in industry settings only when you have large scale data sets. It doesn't cut it when you have small data sets because the statistical properties usually do not show up. The benchmarks usually saturate, and you are not usually able to distinguish the good from the bad algorithms. So it's very important to work with large scale data sets. And this comes with the heavy burden of designing fast and robust algorithms. So if you have a very large data set, you need your algorithm to work fast. You have a very large data set, you can be assured that you'll have outliers in your training set, so your algorithm needs to be robust. So all these things come into play when you're dealing with large data sets, and it's important to keep this in mind. And I think an interesting question that we took from our own research is the question of anomaly existence. Can you quickly, much faster than anomaly detection, determine that there is actually an anomaly in your training set or in your data set in general? That might be a useful proposition in general. Okay, so I'm almost done, but there is one project that we started, we never finished, and I thought I'll present it here. Or the student who did the anomaly detection on video was intrigued by ChatGPT. So this is what he did. This is the prompt he entered. You are an anomaly detection model. And he gave it a few captions and some directions. Okay, hopefully everyone can read the examples. And ChatGPT said, sure, I can help you with that. And it gave the answers, and the answers are remarkably good out of the box. No ChatGPT training, no nothing, just using it. And I'm talking about the original ChatGPT immediately after it came out. And there are a couple of interesting things to note here. One is that it does a decent job. The second is that it's explainable. It gives you an explanation of what's going on. So a tiger seen at a zoo is very likely, and it gives you this explanation. Okay. And since this works, so the next obvious thing to try is to pass a Shanghai Tech video clip through an image captioning module. And I'll play the module just so that the video just so that you'll see the example. So you have some people walking, and then you have a bicycle riding, and this is the anomaly that we'll try to detect. And this is the new prompt that we fed ChatGPT. It has some header, and then you have here for each frame the description, the caption that the caption module provided. And then it simply spits out the result. Okay, so no training required, nothing like that. And it gave you the explanation of why something had a high rank. It explained why some frames were considered normal behavior, and it gives you some explanation of the anomalies. And instead of looking at the results like so, you can look at this way. Okay, so essentially it replaced all the work that we did. Now, I must say that in preparation for this talk, I saw that there is a paper at CVPR this year that is doing something very similar, probably much better. Going forward, I think that we as a community should adopt these large language models and see how they impact the way we're doing anomaly detection. And with this, I will conclude. Thank you very much. I'll be happy to answer questions.
Thank you for the talk. Could you get, please, a few slides before you had like this graph when you try to do the anomaly existence? Yeah, this one. So could you better explain, please, what do we see in the plot?
Yeah. So we know from ground truth there are about 450 anomalous examples. Okay, this is the x-axis. So let's look at 50. This example 50 of anomalous example is ranked about 10 to the fourth, so about 1,000 or 10,000 if you rank all the examples using the Odin rank. So all I'm saying is that maybe I should have used this as the x-axis and this is the y-axis, but all I'm saying is that if you rank all your examples using the Odin score and go them one by one, then after 51 examples, you'll hit a new a patch that consists of a new object class that you have never seen before. And then you as a manual operator, this is a manual step, this is not automatic, say, okay, I didn't know ahead of time that I'm looking for ships, but now I see there is a ship in the data set, and therefore I can decide that this is important to me. I'm going to investigate time and energy, or I don't care about it. And I think that the interesting scientific question is, can you put bounds on that? So to me, this is like a ransack type question, probability versus sampling. How many samples do you need to count in order to be convinced with 99% conviction that there are no new object classes in the data set? And I think that's an interesting question that I don't know if it was addressed before, at least in our community.
Thank you for the presentation. So have you tried this idea of anomaly existence to find the mistakes in the ground truths of the data sets?
I should preface and say this is still work in progress. My students reported, I think, several mistakes. In order to get published, you cannot claim that there are mistakes in the data set. It doesn't look good. So we'll have to stick with the protocol. I think we will have a section or paragraph mentioning the errors that we find. We'll try to do that. But I think this is a useful example. I know that there is a startup company that started by finding, I think, 2 million examples that were wrongly labeled in the ImageNet dataset or something like that. And this goes back to one of the take-home messages. Working on CFAR dataset type things is way too small. You need to be able to handle outliers. You need to be able to be robust to outliers. So you need to work with large-scale examples.
Thank you for the talk. So I have a question with respect to representation, especially let's say we take the case. Okay. For the case of video anomaly detection, for example, for data sets like Shanghai Tech, which is near camera setup, something like pose representation is good. But then if you were to have another data set like street scene, which is a little far field camera setup, pose might not be a good representation. So the only way that I got to know what initial representation is good or bad is by looking at the data set itself, potentially knowing a little bit about test set, which to me feels a little bit of like I'm torn between whether it's cheating to have this initial domain knowledge or not. So my question is, what do you think regarding, should we have a predefined representation that comes from domain knowledge, or is there a case to be made about learning the representation from the data itself?
Yeah, it's a great question that we struggle with as well. I'll say two things. First, you need to be brutally honest about what it is that you want to solve, and make as many assumptions as you want, as long as you can justify them in the paper to yourself and in the paper. So it's fine to say the objects are too small, I cannot run pose estimation on top of that. But say that, don't say that you're not using pose estimation just because of convenience. Say that you thought about using pose estimation, you think that might be a better representation, but you're forced to use pixel values because the data is not there. That's perfectly reasonable thing to say, and I think it communicates much better both with colleagues in academia and with your customers in industry. I mean, they might come and tell you, well, we saw this paper that does it with pose estimation, it gets better results. And you say, that's true, but give me better data, I'll be able to do that, right? So I think being able to clearly state what is the goal and what is the best representation is the first step to doing better research.
I'm little confused regarding the anomaly existence task. Like, if I can tell that there exists anomaly, essentially I have detected some anomaly, right? So how is it different?
So when you do anomaly detection, you're given an image. So think about it this way. An aerial image can be 20,000 pixels by 20,000 pixels. And anomaly detection will require you to label each anomalous patch in the image. But if you can somehow, with high confidence, say there is a new object class in the image, maybe it's a sublinear algorithm, I don't know. I don't know where it is in the image. I just know that it exists. Then you can decide to devote more energy to working on it. It's just like weakly labeled data, right? So you can ask for a very specific pixel labeling of the data, or you can use very weakly labeled data set. I think there might be a hierarchy of anomaly existence versus anomaly detection problems that people might try to solve.
Thank you.
Thanks for your presentation. I have a question about the large language model. Yeah, I noticed that you try to give the ChatGPT some guidance to make it give us a prediction. I want to know, based on your observation, do you think the ChatGPT, if the ChatGPT is good enough to be a good detector for anomaly detection?
The short answer is no. In the longer term, I think it's up to us as researchers to find ways to incorporate what is normal and what is abnormal. And I think this information might be buried within these large language models. And it's up to us to come up with ways to figure this out. Now, it might not be useful for, I don't know, inspection of electronic devices, but it might be very useful when you're dealing with human behavior, because you might have a lot of data. You might have a couple data of text, like news, crime and stuff like that. I don't know the answer. All I know is that I was surprised when the student first introduced this concept to me, and I was amazed when I saw the first results. So there is clearly something there. I don't know how far we can push it.
Yeah, because I also try to use the ChatGPT to do the prediction. I just gave the ChatGPT some examples about some example about what some normal object, and then give another image to make it distinguish if it is a normal or abnormal samples. And I find that ChatGPT is not good enough.
Well, it has these hallucination problems. It's not the solution. All I'm saying, it's another tool that up until now, I haven't seen. Maybe people have tried with it locally, but this year is the first publication that I saw that deals with it. And I can tell you that if I were to work on this anomaly detection in the coming year or so, this is something I would at least look at and try to figure out if there is anything interesting to say there.
Thank you.
I had a question on the representation learning part. So one of the key insights that you made is that it ultimately depends on how good are the representations. One big challenge that I see in industry is that the data set that you can use to train your anomaly detection models are extremely low density. We're talking about single digit images for different types of, let's say, defect detection tasks. And so when you go to industry and you have these real world use cases where there's only handful of images for different types of anomalies, how do you still train models that have good representations?
Depends if you're in industry or if you're in academia. If you're in academia, I advise my students. Okay, that's great. No one can hear me what I'm going to say, so that's actually good. I discourage my students from working on examples where the data sets where the results are saturated. It doesn't matter if you come up with a great algorithm, if everyone is at the 97% accuracy and higher, you're not going to make a dent. So, for example, with the Shanghai Tech, we're still in the 80s. So there is still room for improvement, and you can do. If you're in industry, then you don't have to be fair. You just need to be successful. Do whatever you need in order to solve the problem. I think that there is a very clear distinction here that you need to make. So use whatever augmentation you can think of, whatever prior knowledge that you can come up with. Talk to your customer and see if there are rules of thumb that they're using and try to incorporate it into your loss. Everything is fair game. If you're doing if you're publishing a paper, you need to describe everything in detail and be very clear and honest about it. But it depends where you are in industry or in academia.
Thank you.
Okay, then yeah, thank you very much again for this great talk. And I believe we are having our coffee break now. So I think we'll meet back here in 15 minutes. At 10:40.
Testing. Testing.
What about kind of? But I think it's more like if you kind of hit here.
Testing.
Test, test. Oh, it's working.
Testing, testing, testing.
Excellent.
Ja, klar. Ja, sag kurz was. Hörst du mich? Hörst du mich? Ah ja, ja.
Genau, da kann man
Hello. All right, everybody, I think we can continue. And next up, we have a paper presentation from Darsol Choi, I believe, is presenting. Yeah, you can just come to the front. All right, and take it away. Yeah, the presentation is. You sent PP the PowerPoint, right?
Yeah, this is.
Yeah, here it is.
Hello, everyone. My name is Dasul Choi from Yonsei University. Today, I'll be presenting our work on. Okay. I'll presenting our work, disentangling marginal representations for out-of-distribution detection in collaboration with Dongbin Na. While deep neural network models perform well in the trained in distribution data, they show overconfident problem for out of distribution data. For instance, consider a classifier trained to identify members of BTS. It confidently recognizes V from BTS. However, when the image of Jenny, not part of the training data, is mistakenly presented, the model sometimes incorrectly asserts it's one of the members with high certainty. Ideally, the model should indicate uncertainty showing an equal probability across all classes. This overconfidence can lead to serious issues, especially in security and safety applications, highlighting the crucial need for robust out-of-distribution detection. So OOD detection essentially functions as a binary classification test, determining whether an input deviates from the expected data distribution, as illustrated with the image of BTS members, which represent our in-distribution data. Any non-member images automatically falls into the OD category. The challenge, however, lies in the vast diversity of potential OD samples, making it impractical to fully represent or collect them in a data set. Turning to the related work, we categorize OD detection method into three main types: post-hoc algorithm, outlier exposure, and synthetic OD data generation. Our method falls into the third category, which involves generating artificial OD samples. Specifically, we employ marginal features to rely on marginal feature to enhance detection capability without relying on real-world OD data. So our method, disentangling marginal representations, utilize a latent operation in the latent space to disentangle marginal features from the original image. We start with encoding, converting images to latent vectors. Next, we manipulate these vectors by extracting and modifying features unrelated to their classes. Finally, we synthesize new samples by combining these manipulated features to generate effective OD images. In our approach, we first extract marginal representations from data by leveraging the class representative feature. This is achieved by subtracting the mean latent vector of the class from the encoded image vector, allowing us to isolate and utilize features that are not class discriminative. In this equation, lambda adjusts the influence of the marginal features. E of x represents the encoding image, and mu of y is the mean latent vector of the class y. Next, multiple latent mix-up is a technique we use to synthesize artificial OD training data. By mixing encoded latent vectors and adjusting the mix-up parameter K, we control the diversity of the resulting OD data. This allows for a richer variety of OD samples, crucial for effective training and robust detection. The picture on the left are the multiple latent mix-up without DMR, and the picture on the right are with DMR. As you can see, the pictures generated by our method lack crucial features of their own class. Finally, our rejection network is trained to differentiate between ID and OD data. It assigns a 0 for ID samples and a 1 for OD samples, employing binary cross-entropy loss. This network analyzes feature vectors from a frozen feature extractor, which means it does not alter the original classifier's weight, ensuring the base classification performance remains unaffected. In our experiments, we evaluate OD detection performance using CIFAR 10 and CIFAR 100 as our ID datasets. Additionally, we utilize OD dataset, including texture, LSU, and crop, tiny ImageNet, SVHN, Gaussian noise, and base 365. So in our training setting, we utilize model architectures, including WISE ResNet, ResNet, and DenseNet. For training rejection network, we employ the two-layer shallow MLP network trained on 50-100 ID training images and synthesizes all the images. Training spanned 10 epochs with learning rate of 0.01 and a momentum of 0.9. The mix-up parameter K is adjusted to optimize the diversity and effectiveness of the synthesized OD data. For evaluating OD detection metric, we used AURC and AUPR. So this is our results compared with our baseline methods. So the upper section lists the post-hoc approaches and the lower section covers the data generation methodologies. As you can see, our method achieved the highest average performance in both AURC and AUPR metrics. And here are the results compared to outlier exposure, a method that relies on real-world external OD datasets. Our approach DMR demonstrates superior performance across a variety of datasets, and notably enhances performance on a CIFAR 100 benchmark when integrated with the Kirby, previously considered a state-of-the-art method. However, our study has some limitations. We have primarily experimented with simple data sets, although we conducted experiments on more complex data sets like ImageNet. We could not include them due to the submission deadline. So in the future, we plan to expand our approach to more diverse data sets and aim to explore advanced techniques. So in conclusion, our DMI method not only simplifies the training process, but also establish a new standard in OD detection, leveraging marginal features to effectively challenge and redefine classification boundaries. Thank you for listening.
Thanks for the presentation. So how are you sure that the disentanglement has worked properly?
Sorry, one more time. How?
So you said I disentangle the data so that I have just some features that are not related to the anomaly label, so I can generate multiple samples. How do you know that the disentanglement has worked properly?
Just we experimented with, yeah, compared with other data sets. So basically, so theoretically, we couldn't find out the logic, exact logic. But yeah, by experiments, we found out it outperforms. So we will define about that later.
Okay, okay.
Thank you.
Could you please go back to the slide that you showed your loss function? Okay. I have a question. So what other types of loss functions did you try, and why didn't you use focal loss, for example, when you have imbalance in your data set?
Imbalancing, we selected the same numbers of pictures. So I mean 50, 100 of ID and 50,000 of ID, 50,000 of OD. So yeah, so we thought that just binary classification would be better.
Thank you. Next up, we have our keynote speaker, Dr. Chin Liu. She's an assistant professor with the University of Alberta and Alberta Machine Intelligence Institute Fellow. She received her bachelor's degree from University of Peking and her PhD from University of Toronto. Her research interests lie at intersection of machine learning, computer vision, and AI for data analytics. And her recent research focus is on reliable AI, particularly anomaly detection, model robustness, and model adaptation and generalization. Okay. And so a quick follow-up after the keynote, her PhD student was unable to attend to give a spotlight due to visa issues. So she'll be presenting on behalf of her PhD student as well for the spotlight. Thank you.
Okay, good morning, everyone. So thank you for having me here. So in the next 1 hour, you're probably bored by my voice. I'm sorry. So in this big talk, first we will talk about our recent work in anomaly detection. The title is Beyond Conventional One-Class Anomaly Detection. So it means that we extend one class the anomaly detection to multi-class anomaly detection, as well as the zero-shot innovations. So all of this work, the recent update from our groups, and we welcome any questions, and either after the presentation or during the presentation. So in this morning, we have talked about what is anomaly detection. So I'll briefly go through the background. So it's majorly the anomaly detection refers to the detect anomaly distance difference from the normal populations. So the normal population usually represent the majority of the distribution. So for anomalies, we say that either we try to estimate or regret the anomaly score for samples. So this is the traditional definition of anomaly detection. And then later on, recently, we see that in addition to anomaly scoring, we also want anomaly localization, which means that given the discriminative models, we also want to localize where is the anomaly it is. So because the anomaly is usually considered as the data deviate from the normal cases, so we say that they distribute a large range of unknown regions or unknown spaces in the latent space, we don't know. And also it's very hard to collect the data. So instead of saying that we collect normal data as well as the abnormal data, we usually right now focus on the data efficient setting, saying that, okay, we assume that only normal cases available. So in this presentation, we will talk about a little bit about what if we have a few shot of abnormals. Can we extend our one-class modeling models to that scenario as well? So we say that in such unsupervised anomaly detection is very interesting because actually there are several reasons I listed here. So from the perspective of data collection, we say that normal data usually are easy to collect because normal data usually reflect what happens during our normal considerations or normal situations. Instead, abnormality usually rare, and it's very hard to connect, especially, for example, for medical data set. For medical, we say there are some real case or some real disease. It's very, very hard to collect. We can't contain them in our training data set. However, for the supervised learning or for a lot of traditional machine learning, we say it's a closed set problems. So we want to formulate the problem as a the open set problems. So that is from the consideration of the data collection. And also from the learning difficulty perspective, we say that usually normal data share normal patterns. So all these patterns are compact. If we can learn this compact representation from a vastly of the normal, it's probably easier than learning directly from abnormals. And thus, we say that this unsupervised anomaly detection may appropriate for a lot of real case. For example, here I give two examples. On the left is OCT images, which are about the eye diagnosis. So you can see that for most of the cases, normal sample share quite normal, the slim shape. But for the abnormal case, it can have bump, it can have some different little abnormalities. And on the right, I think on the left, and anyway, left to right. So on the other side, we have a histopathology. And when we say histopathology, tumor, so usually the doctor will tell us that, okay, different person have different appearance of the tumor in cellular in the cells level, and we say that the abnormal cases usually heterogeneity in morphology as well as size. So in terms of learning and data collection, we say that unsupervised anomaly detection is more feasible. So that's why in this talk, we mainly focus on unsupervised learning tasks. And regarding applications, I think you already know that we have industry inspection, we have medical, we have video surveillance and different applications. So I will skip that. And despite different applications, actually, in my group, we summarize the principles to design different anomaly detection solution. It's more like given different data, especially given the normal data, it doesn't matter what kind of modality it is. The key point is that we want to train the model. This model exhibit very consistent performance for normal cases, which is a training case. And then the model also have the capability to amplify its response to the abnormal case. Give a very strict example for example, for reconstruction-based paradigm for anomaly detection. We say that usually we assume that normal case can be reconstructed perfectly. If it is not perfectly, then wishes the reconstruction error is very small. And for the abnormal case, then on the other hand, we want reconstruction error as large as possible so that the reconstruction error actually corresponds to the real case. So this is a typical example of what we mean by build a model, amplify the contrast response. And based on these principles, actually, we have different solutions. For example, state-of-art usually build one model for one classifications. So, which means that here, I'm sorry, I forgot mention. Okay, anyway, so forget about it. At the very top, it's my, I'm not sure if you can see, at the very top, it's my representation structures, but anyway, it's just hidden. So for the second part, we talk about state-of-art of one class anomaly detection. So usually the most of the state-of-art actually corresponds to this paradigm, which means that we usually need to train one model on a particular class. If we have a new class, we need to retrain the model, tune in the hyperparameters to get a good performance. So this is the traditional way. And based on the literature study, we categorize the current one class, the anomaly detection into 5 categories, which is the one class the A, one class classification, which is more about to project all normal case onto a compact regions in the latent space. For example, the traditional SVDD and deep SVDD. And then we have a normalization flow models, which is estimate distribution of the normals. And then we try, given the abnormal, we see, okay, its distribution is different from the normal distribution. And C is teacher-student model. It's more recently, we leverage the knowledge distillations, which means that we have a pre-trained teachers. We want the student to mimic the behavior of the teacher based on the normal case. And then for the abnormal case, the student kind of show different response. For memory banks models on D, it's more incorporate memories to record the prototypes of normal. And then we try to reconstruct or compare the queries into this prototype in the memory. And last is the classical reconstruction models. So, but all of this paradigm actually can be applied, or most of the state-of-the-art method are actually be one or combination of one or two or several the design philosophies. And in this talk, we will talk about knowledge distillation as an example. So knowledge distillation means that we have a teacher student, and for the teacher, usually it's pre-trained. It have a very power representation capability. And for the student, we train the student using the training case from the target subject. And then we say during training, only normal data experience the student so that the student can perfectly recover, or we say not recover, perfectly mimic the representations of the feature. And thus, during test, if there is an abnormal case, we say that the teacher will show different behavior. For example, the feature extract from the trainer, from the student model pre-trained on the normal data looks different. And because of the tradition, in A is the traditional knowledge distillation, and in B is the reverse distillation we published in 2 years ago. It's a long story. But anyway, for the B, reverse distillation, it's still, we train the students to learn the model from the teacher, but at the same time, we introduce this bottleneck. So which means that the inverse means that the data flow is different from the vanilla knowledge distillation. The data flow coming from the image or the raw data, from the raw data to low dimensional representation. And we feed the low dimensional representation to the student to recover the features. So in detail, it's more like this bottleneck, low latent space, act as an information bottleneck. In theory, this information bottleneck is trainable so that it can preserve very, very essential information in the normal case. At the same time, it can prevent the abnormal features flow to the student model so that it amplifies the difference between the teacher and student. And following the traditional knowledge distillations, we just compare the channel-wise representations. If the teacher channel-wise representation and the student representation are very, very similar, we say it's normal, otherwise it's abnormal. So this is just a performance of the reverse distillation. Why we want to talk about reverse distillation? We will show that this model also have a very wide capability to extend to different scenarios. So, and before that, this is the general case for reverse distillation for unsupervised anomaly detection. We apply them to the MBTech, the VISA dataset, which is the benchmark for the industry in visualization. And we also apply to medical for the anomaly detection. Here we just show the anomaly localization. So you can see that compared to a lot of the PNET, by the way, the PNET is a particular anomaly detection method designed for the OCT dataset. The rest from patch call to ours is the general anomaly detection method. So you can see that even though most of the state-of-art method here, the patch call, C-flow, the padding, MKD, and the reverse distillation are proposed for the general anomaly detection for nature images or the industry inspection. But when we apply to the medical data set, you can see the localization is quite poor compared to the ground truth. But the anomaly detection is quite good. And the patch core is also very good. And then we say that, okay, given anomaly detection, we believe it have a capability to extend. We try a further scenario saying that, okay, at the beginning, we have unsupervised machine learning. So which means that we only have the normal data. And then after some detections, we collect a few anomalies. So will the performance of the reverse distillation still continue full step? So we do a test on the histopathology because usually histopathology considers very difficult task for medical imaging, especially for anomaly detection because of the heterogeneity of the representation of the cell distribution and morphology. So we do two different modifications instead of untouch the model itself. First, we say that because we have a few anomalies, so we first follow the original reverse distillation, we minimize the loss for the normality samples during training the student model here that represent SD and also the bottleneck, but the teacher is still frozen. And then we maximize the loss for anonymous. So it's quite easy. So we want the representation close to the normal and amplify the difference, as we said, the principles, design anomaly detection. And at the second time, we say that because the anomaly is just few compared to the normal case we collect, so we need to upweight their loss corresponds to abnormal case so that the loss can reflect normal and abnormal cases. And just with these two small modifications, let's see the performance. So in whole slice imaging, we make the normal case for training and abnormal case for training as a 1:10 ratio. And here is an example of the whole slice imaging of abnormal detection. And B is the ground truth. C is the state-of-art fully supervised method to localize the anomaly regions. And F is our improvement, it is our results. And D and E corresponds to the state-of-art weakly supervised method. So you can see that even with the small modifications on reverse distillations, so that we extend reverse distillation to weakly supervised, it can boost a lot. Particularly, this is the numerical. The green and the yellow corresponds to fully supervised one. So we still see a lot of gap between the fully supervised one is expected. But compared to the previous the weakly supervised, we already beat them with a simple modifications. And we're curious, okay, how good, how bad if we increase or decrease the few shot of abnormal. So we do an ablation, we start at 0, which corresponds to vanilla reverse distillation, or we say vanilla unsupervised anomaly detection. We calculate the patch classifications. So it's just beyond a little more or less than the random guess of 50%. And then we just increase 5% 5 patches versus 5,000 normal patches. We increase 10%. We increase to 10, just 10 samples. We increase. And once we get the 100 or 500, we almost saturated. So oops, it seems it's run out there. Okay, doesn't work. Okay, it's tired. Do we need it? Or, yeah. Okay. Probably battery. If there's questions, right now it's the time, probably.
Test.
Okay, it works. Okay, I think probably it's too much for one class. Everyone knows that. And this microphone just remind me. Okay, done. So let's talk about third, the beyond. So what is beyond? We say that for one class modeling, it's good performance. For example, for some benchmark, for example, the MBTech, 99% right now. And for the visa, I think 98, if I remember correctly. And easy adapt, we show that at least reverse distillation is very easy to extend to weakly supervised scenario. Not all of the algorithms, but part of them, at least, reverse distillation. But we say that what if we have multiple subjects? What if we have multiple categories? For example, we extend to hundreds. Can we train hundreds and keep hundreds? Probably not. So the model scalability is an issue for most of the state-of-art one class. Then we say that, okay, different from the recent train that train the different multi-class models, which means that we train one model on multiple class together, and during test, we directly feed the samples to the model, and it can tell us, okay, is the query, is abnormal or normal, and what is the abnormal scores without knowing its category labels. So then with that, okay, it's still design a model for different category, but giving a lot of state-of-art of one class anomaly detection, can we still extend it, reuse them? So we do an application study. Here, RS corresponds to the reverse distillation, and the FD means that forward knowledge distillation, which represents the still state-of-art methods. And the triangle here, I'm not sure, I think, okay. The triangle here, for example, corresponds to the one class modeling. When we directly apply this method to multiple scenarios, we see performance drop from here to here. And similar for the forward distillation from here to here. And then we think about, okay, what factors leads to this performance degradation? So does it mean that all previous existing one-class modeling does not fit the multi-class scenarios? Can we reuse all whatever we already got for the multi-class to realize a high scalability? So we investigate this and we try to improve it to the new star, which is the multi-class. And our proposed algorithms not only boost the multi-class, we also boost the single class modeling for anomaly, for knowledge distillation based method. And we expect the philosophy can extend it to different one class anomaly detection. So after some study, we found that, or we believe, cross-class interference is one of the major issues. So here is a visualization example of what is cross-class interference. So here in this figure A, we say that if we have two categories, and for the one class modeling, we just need to model the distribution, for example, in the latent space about the distributions. And then anything outside of this compact representation regions can be considered as the abnormals for this particular class. However, when we train to model of multi-class, we found that the one model needs to fit the joint distributions, which means that there were some overgeneralization regions in the middle. And this overgeneralization region in the middle actually caused the performance degradation. Then the solution is quite straightforward. If we can identify the labels, then we can formulate the one class. But we can't, because usually for multi-class, we assume that we know there are 5 or 6 categories, but we don't know exactly label during query. If we need query, either we need human annotation, human intervention, or a discriminator model telling us what is the label. So we rely on other models. So can we have an automatic method to extend all this single class to multi-class? Then based on the image processing theory, we found that actually the structure information in images actually explicitly tell us what a category, what is the semantic information it is. So for example, what is structure information? So structure information can be considered as the pixel structures or the regions, the different local regions interaction to construct the whole images. For example, consider dog. It have ear, it has a nose, it have an eye. Instead of saying we only consider ear, eye, we consider the global distributions and relationship between eye, ear, and color together. So which means that the structure includes the local structure of the pixels or semantic information as well as the global information. If we can constrain the student learn the structure information from the teacher for normal cases, then probably this learning can constrain the student's model to less overgeneralized. And therefore, for knowledge distillation-based method, which has a teacher model and student model, instead of saying we only enforce the channel-wise similarity between the teacher and student, we also consider the correlation or the concurrence relationship between channel features within one channels. And also, we consider affiliation representation, which means that the global representation, which means, for example, as the features that have the largest values, whereas the lowest values in the representation. So together with this structure information, we just need 3 more loss in training student. We can boost the performance to constrain the semantic information to incorporate in the multi-class knowledge distillation. And on this demonstration, we just use a cut and paste to synthesis of normal case. You can see that in the middle is a table and outside is just a device. And in the traditional anomaly detection, we say that because we just compare the channel-wise features for knowledge distillation, we cannot roughly, we just can give some abnormal regions, but generally the pixel level anomaly score is still low. But once we consider the semantic consistency in terms of the structure information in distillation, we can see that the whole samples here actually is abnormal. And also, we use this SNL on the real case. We can see that the abnormality here also highlighted because it's also considered the neighboring information as well as other semantic information from the normal case. And this is the roughly structure of the whole algorithms. So the LCD first here is just the vanilla knowledge distillation loss to map the channel-wise feature similarity. And SD is the semantic information, as we said, structure information, intra and inter as well. So they represent different numerical evaluations to train the student model, and all the rest of the story exactly the same, including the model itself. It doesn't matter, it's forward distillation or reverse. And during the test, we consider the vanilla, the original loss as anomaly score as well. We also consider the semantic so that it can compress or to accommodate the multi-class anomaly scores. I'm not sure. Okay, it's not that obvious, I think. Anyway, so here is 4 figures. I'm not sure if you can see the SNL, this line and this line. So in these figures, we compare the multi-class anomaly detection. Uni-AD and Omni-AD is the recent multi-class anomaly detection methods. Both of them are constructed based on the new models in terms of the transformer-based reconstruction models. And for the forward distillation and reverse distillation, we keep all the model structure the same except the training loss. As we said, we add 3 more to reflect the structure. For the localization, the 1, 2 on VISA and MBTAC, you can see that the performance generally improve 5 to 10% for the multi-class. And for the single class, it still improved the performance. This is the localization performance. This is anomaly detection. This is detection. This is localization. Just with 3 boosts to combat the cross-class interference or inter-class interference. Actually, many single-class modeling for anomaly detection can be extended to multi-class cases, which means that actually we have more extension to do using the state-of-art single class. And this is just the visualization examples for single instance, which means that for single class, we can see that including the structured informations, it helps to accurately localize the information. And for the multi-class, it still improves the performance. But the thing is that for this multi-class investigations, although we see the promising performance, but we still see actually there are some performance gap from the one class modeling, which means that in addition to the interclass interference, we probably need more constraint on the models so that it will not generalize too much to different categories. Though this model partially adjusts the challenge of model scalability, we say that if there is a new category of object comes out of this n categories, we still need to retrain the models. So then we're curious, okay, what if? Can we have a highly scalable one-fit-all models? Can we? So then regarding this question, our first answer is probably yes, the zero shots feels good because for zero shot, generally the concept is we don't need to train model. Once we have the model, we can do the classification or we can do the anomaly detection. Okay, then how can we do this? So currently in my group, we categorize current state of art into 3 different paradigms. The first paradigm is that directly use the training data set. For example, we say that we have good models. And if we want to do the one-fit-all models, which means that the model just directly learn during testing time. And how can we get any reference without training? So the first paradigm that whose representative work is the music, I think published this year. Last year or this year? This year, I think, the music. For the music, it says that given the query testing data set, they come from the same class or different class, but most of the image patch may contain normal informations. So if we can compare the normal informations in the image, even though the whole image may contain anomaly, they give a reference to each other. But this method in A have a big problem is that it cannot realize real time and at the same time good performance. It requires go through all the distribution of the testing data sets and see, okay, what is the majority distributions. So the second paradigm here is using the VL model, vision language model. We say that, for example, CLIP. This is the most most of the zero-shot learning methods right now follow this paradigm. And we, in addition to B, we further explore to see, okay, what if we combine all available information in terms of the test data set, we pair all the test images at the same time, we use the language model as a reference. Can we boost the performance? Which means that we try to explore all available information for this zero shot or for this highly scalable because we cannot train the model before. Then during test, we just try our best to use all kind of modalities. And let's first talk about using the VR model. So this is CLIP. So everyone knows that CLIP build a correspondence between the image and text. And therefore, the naive way to do this is that we just give a positive and negative textual prompt. And then given the query data, we just feed the data to the encoder and compare the similarity, get the positive or negative similarity. And depending on the similarity, we just got whatever the performance. And this is the general case. And then we say that when we apply the CLIP model for the naive anomaly detection highly scalable solutions, the text encoder and the vision encoder usually trained the original CLIP, for example, trained from the internet. So the text may not reflect the domain information. And therefore, we say that for the textual information, we want a domain well state prompting. For example, we know once there is a query data, we know it's industry or it's manufacturing or it's vision visualization, the vision visualization or medical photo and normal and class. So in this way, we somehow get some text encoders that corresponds to domain information. And then we compare the similarities to get the anomaly score. And then what's the problem? The problem is first, the clip was trained to do the classification, which means that usually for clip, we usually say it's a cat, it's a dog, an image of cat, image of dog. So if we are given, for example, a hazelnut here, we say an image of hazelnut, it can tell the hazelnut, but it may not tell it's bad hazelnut or good hazelnut, which means that the clip model originally was trained for the global description rather than the local. So, but we say that anomaly detection, especially anomaly localization, usually refers to the fine-grained task, which means that we want to know where's the abnormal it is. And the second is domain gap. We say that we incorporate the domain information in the texture, but for the images, we still don't have such any information for the domain gap, for the domains. So how can we do this? Towards the first challenges, we use the VV attention proposed in the clip surgery. So it says that without training, given the original clip models, we directly extract the V for each values and then try to calculate the VV attention. This VV attention most focus on the local descriptions. The reasoning behind is that if a clip model can tell what is cat, what is dog, it has to know what is dog and cat, which means that it may have already contained the knowledge of the local information, but its representation is not for that purpose. So the VV attention is just extract to the local informations. And this is how we address the first to fine-grained description. For the second, we say that we have the domain texture prompting here, but the text is okay. But how about the image? We still have a domain shift. Then for the domain shift for extract features, we design a test time adaptation method to adapt the VV attention, the representation to the input images by self-supervised learning. And after that, we combine two together, get a quite promising framework. So compared to the wing clip, which is the winner in last year in this competition, and also clip and the mass clip trans-M, we can see the Anoclip is the good. And Anoclip plus, which corresponds to Anoclip plus our test time adaptation, boost the performance further. For the localization, still quite similar. So this is the performance. But here is not the end. We say that compared to the full shot, it still have about more than 10 point, almost 10 point difference performance gap. So how can we do this? We say that Anoclip or the NOVL provide a very, very good benchmark because it won't introduce too much. One is VV attention, so there is no training at all. And we also have the prompting texture. So they form a very, very good benchmark or baseline for zero shot. Then the next step is we want to explore if we can use the test data set to boost the performance, because we say is we want to have a highly scalable models. We want to explore as much information as we want. And for the test set, so in this figure is the whole slice dual image enhanced clip. So in the second half is exactly the same. Clip models, text encoder, get the representation, compare the image representation, get the anomaly score for the clip from the text. And also the top branch is here. The top branch is very similar to music, except we improve it in terms that instead of go through all the training data set, we just randomly pick two. Even though the pick two can be very similar, it still can help us to get a good reference. And based on combine this vision and the language, we also further design a anomaly synthesis strategy to bridge the domain gap. And combine these three together form our final zero shot anomaly detection. And here is an example of why the three branches works. So first, the AL, the localization, this one corresponds to the vision localization by language only, which is the original clip, the NO clip model or NOVL model. We can see that based on the large language models, the method have a capability to localize the abnormals. The second line corresponds to the methods only rely on vision, which means that we only sampled one text image as a reference to calculate anomaly scores for the queries. And for some cases, you can see there are some difference. If we combine them together, we can perfectly allocate, which means that the pre-trained models, particularly CLIP, contain a lot of information. At the same time, the training data set itself can reflect some normal distributions. If we combine them appropriately, they can boost each other. And this is the final performance. We include the music too, which is the latest work, only rely on the vision. Two means that only two, we randomly sample one samples from the test set as a reference. So I can see the first hours is directly boost the clip using the test images. And hour plus is the model with the test time adaptation. So you can see that both leverage all information actually can boost the performance. And also, this model is highly scalable just with the pre-trained foundation models as well as test time adaptation, which means that we don't need to train. But what is we don't need to train before deployment. However, we still see some gap between the fully shot and zero shot. So the zero shot music here, you can see it's very high because it goes through all tested data set. We list it here because it's probably give us, I think, the upper bound of the zero shot performance. But because the music model goes through all test set, it cannot realize real time. And for the rest of zero shot, it's far from short from the UniAD, which is a multi-class model, as a DREAM, which is a synthesis model for one class modeling. So you can see that we still have about 4 to 5 performance gap between full shot. And therefore, we say that our next step is to improve the performance of these highly scalable models. First, we see there are performance gap from the full shot and the few shot modeling. So we probably will try the few shot and full shot to see, and also the weekly supervised scenario to see, okay, if we can improve the performance. The second one is it's observation in the foundation model applications, saying that in the foundation model, especially the multimodality, the textual prompting actually have bias. How can we debias? Because we say that design different promptings and it may bias the representation of textual representation and finally bias the final similarity score between the texture and images. How can we do this debiased things for different categories? It's also future work. And finally is sum up. So in this talk, we talk about several advanced exploration in my group. So we start from the one class anomaly detection, focus on improving its scalability and reuse of one class modeling methods. And we found that inter-class interference is one of the major issues for the multi-class modeling. So we propose structures. However, though the performance is good, but however, the scalability is not still that satisfied. So we turn to the zero shot and we leverage language model as well as all available resources, including the query data. in the testing data set to improve the performance. And there are a lot of things to do in the future to improve the performance because we already see there's still 5 to 10 performance gap, even on the benchmark and not regarding to the real cases. So that is all about today's talk. Thank you very much. Now here we go. Thank you. I'm sorry that, okay, is that boring?
No, it's a very exciting talk and very interesting and very interesting work. I'm wondering about the early in the talk, you were talking about the reverse knowledge distillation as a mechanism of improving the anomaly detection.
Yes.
And I was wondering, is that method also capable of performing anomaly localization or extensions of that method? And how would you go about trying to do something like that?
Okay, it's very nice question. So let's look at these pictures for reverse distillations. So in reverse distillation, we said that during training, the student is trained to reconstruct the features for each early layers of the teacher. And during training, so, oops. Okay, it's again. So hopefully, can you hear me? Or no? It's good? No? Okay. It's fine. I can go there. Thank you. So we say that during testing, so we compare, okay, here is example. It's much easier. So for in these figures, in B here, the blue corresponds to representations of the teacher, and orange corresponds to representation of the student. So we know that the student try to learn the representation of the teachers. So for each of the features, we compare the similarity. If the similarity of the teacher and the student representation are very similar, we say that the query highly probably it's normal because the student model is trained to reconstruct, to mimic the teachers. But if they are different, for example, here, highlighted as the rectangle, the regions. So we see that, okay, for this one, the teacher may behave different from the student because in this reverse distillation, here is a bottleneck, which means that most of the abnormal information actually may not pass this bottleneck because this bottleneck is designed, trainable to pass the normal information. And therefore, it means that during deployment corresponds to the abnormal cases here. The student is still trying to reconstruct these features based on the normal information or majority information from this bottleneck. So there is a big representation discrepancy between the teacher and student. And therefore, it helps us to detect if it is normal or abnormal. Regarding to the localizations, as you can see, we compare different layers, multi-resolution layers. And thus, we can somehow upsample the representation to the original images and give the roughly location. For example, for this representation, it's not channel, it's location, spatial location, roughly which regions corresponds to this discrepancy. And thus, based on this discrepancy index, we can allocate where is the abnormal comes from. So that is to say for for reverse distillation, even though we just train the student model to mimic the teacher student, it can realize anomaly detection as well as anomaly localization. So I'm gonna answer your question. In the final embedding, so you mean the final embedding, you mean here or here? Here. So here is the thing, because the student try to reconstruct the teachers during training. So, and here the bottleneck is very high dimension. So it's behave like information bottleneck. Only the most essential helpful information to help reconstruct the features will pass through. So this is how we train the bottleneck. And therefore, during test, if there is an abnormal case, the abnormal case, if it is small, it will be prevent passing through this information. And therefore, it's amplify the difference between the teacher and student. Yeah, thank you.
Yeah, okay, let's take one more question and then yeah, okay, good.
Thank
It's a
you.
quick question then, yes.
Very quick. Great presentation. Thank you very much. I agree that the CLIP models we have used them in the past for some real-time applications, and they're really generalized. They're really good at generalization. We've tested on several industry applications. How do you see this, like the new approach of combining the vision and the language being deployed into a real-time application?
Okay,
Yep.
it's very nice question. So for one thing, I think let me answer your questions in two ways. First, regarding the application scenarios. So when applications, we say that, for example, think about the industry line. If we don't know, if we know nothing, we just collect the data. So that is to say, at the very beginning, we may not have the query or just one. And therefore, the textual information provide very initial information. And if we have more images comments, it doesn't matter it's normal or abnormal. If the abnormal is different, which means that the rest part of the image can be a reference for each other. And of course, someone may ask, what if the abnormal case is very, very similar? So it's fine. In that case, it's in an extreme case, the whole method just simplify, or we say it's equivalent to a just clip model using the text as a reference. So that is to say that using extra information in the test set is just a bonus. It's leverage more data, but we cannot guarantee. But in most of the cases, we say abnormal is different. So that helps. Thank you.
Yeah, then thank you. Thank you again.
That's one.
You're getting a lot of applause today. Wow. That's good. Yeah, so welcome the new speaker. Yeah, stage is yours.
Thank you. Because my student have visa problems, so I need to present for her. So in this talk, it's a bit of different from the previous one. The previous one is more technical, and this one is about the benchmark. So in this presentation, we talk about collecting the data for medical anomaly detection, and all the resources I talk about today is already online in this GitHub. You can find all resources there. And first, we talk about why we need a medical anomaly. So we said that the industry anomaly detection, we have a lot of benchmark, the VISA, the MBTech local, and so on and so forth. The second application or typical application is the video anomaly detection. So for the video surveillance anomaly detection, we have the Shanghai Tech, the Avenues, the UCSD PAT2, and also for recent 2 years for the NIPS dataset benchmark, we see more and more video anomaly detection dataset comes. So about the third one, medical, do we have any? No. We found that in my group, I asked my student to do the medical anomaly. We found a very interesting thing. So given the same topic, and we found that the citation is totally different. They refer to the same data set, they cite the same results, but actually after digging, we found that the citation is not correct. And we found that for medical anomaly, right now, people use their own private data set or directly refer to the data set, their curation. but the citation errors as well as the citation errors as well as other factors actually we think is the major challenge we need to tackle to boost the performance. This is the first reasons motivate us to curate this medical anomaly detection. The second one is that, as my previous presentations, we see that there are a lot of advance in the nature image or the industry image anomaly detection. And when we apply this detection method on the medical images, performance varies. So we say that, okay, what if we build a benchmark to evaluate all this performance and to see how good or how bad it is? For one thing, it helps to improve the medical anomaly detection because we said anomaly detection in medical actually may correspond to real case detection, real case diagnosis and discovery, and also new knowledge discovery. And the second is that for medical anomaly itself, it also helps boost the performance. And third, it's also boost the performance of anomaly detection in general purpose, the methodology development. So we said that, okay, if there's no one, we build one and publish it. So this is the overall view of the BMAD. The name is Benchmark of Medical Image Anomaly Detection. We give it a BMAD. We are so mad that there's no medical benchmark, and it's so lag behind compared to others. So in this data set, finally, we construct 6 benchmark coming from 5 different image modality from 5 different organs. And we also provide a very easy to use interface to support state-of-art 15 different methods. And they are select from different paradigms. So you can try different methods. For evaluation, we provide the codes to evaluate the image level AURC, the pixel level AURC, as well as the per region overlap, which is account the smaller anomaly regions. So we will talk one by one so that you will get more information about this benchmark for your future use. For the data set curation, we have 3 considerations. First, we know that different from the general, the nature image anomaly detection usually use the RGB data set or RGB image modality cameras. For medical images, they have different image modality. So this benchmark try to cover as much as possible. So it includes a CT, MRI, histopathology, OCT, and so on and so forth. Also, we can see the different modality. We say that different modality may show different abnormal appearance and semantic. We want to build a benchmark that can accommodate as much as possible. Third one is for usability. So because there is no such medical data set designed for this purpose, we need to remix, reorganize, cleaning, and redistribution this one for the community. So we consider to curate this data set from the previous challenge and public data set to make sure the license is free for us to use. And therefore, based on these 3 considerations, we finally come with the MRI, liver, retina, chest, and pathology. And most of the data set are coming from the public and, oh, I forgot to mention that. All these data sets are no commercial use and share likely, which means that you can reuse it for free, generally for research. And most of the training contain at least 1,000 of normal images. And the test is quite large compared to the most medical images or private data set. And 3 of the data sets support segmentations, which means that 3 of them support pixel level annotation for the anomaly localizations. And 3 of them only support pixel level, the sample level. This is roughly look like the examples. So the CT, MRI, X-ray, and you can see that the content varies differently. And for each of the data sets, because we need to remix, and sometimes some of the original data set is classified, is published for segmentation and classifications or 3D dimensional. So we do a lot of data cleaning, selection, and remix. And all this pre-processing has been published, which means that not only for this anomaly detection, these pre-processing steps can be used for all other medical image analysis utility. And for the Curie dataset, the 6 benchmark, the all data is structured in a similar structure. So for example, take the brain as an example. We have when you download it from the Google Drive, so it has train, validation, and test. And for the training, we only contain the good, which means normal images. For the validation, we have good and ungood, which corresponds to the normal case or abnormal case. If the dataset support the pixel level annotations, then we say that we provide an anomaly mask. Otherwise, there is no such anomaly mask. And all 6 datasets structured in these structures. So it's very easy to use later. So this is a dataset about the method. You already see this one. I stole this one from these papers. So for 5 different categories, we select the latest representative since last year. And when you train the model, you have 3 different ways to use these resources. So they are structured under one interface. So if you just want to use the models, so you just use test. We publish all checkpoints here, and you just need to say, okay, you want to test the checkpoint. What is the data set? What is the method? Here is the pattern. And what is the weight, which is published. Then you can just directly run the code to get the results. If we want to train the model from scratch, you can just run the Python main train the data set, which data set you want to train, and the models. If we want to query your own data set, it's fine. Follow the same structures and use the interface. You can run all the 15 methods. And also, some people curious about the hyperparameter. How can we evaluate? So in this benchmark, the current research, the current results are based on the original model design, which means that we don't have a heavily hyperparameter tuning, which means that actually the performance may not optimal for each particular models for each particular data set. So if we want to change the hyperparameters, just open config files and change all the parameters for each of the model, for each of the data set. We have a specific hyperparameters already there. So just try to find the one to modify and train the model. So it's very easy to use right now. We try our best to make it a convenience because my students suffer a lot when we reproduce the previous methods. And last, about evaluation. So for evaluation, we consider sample level, pixel level. We hope that it's threshold independent. Otherwise, for each method, each data set, we need to tune a different threshold. It's unfair, we think, for benchmark the performance. So finally, we end with AURC and the PRO. PRO is the per region overlap. Why we need this? Because different from a lot of recognition and segmentations, anomaly sometimes very, very small. And if there is a large region anomaly and small region anomalies, the loss or the calculation evaluation, the large anomaly would overwhelm by the small, but sometimes small is important. So instead of directly use AURC, we use the per region overlap, which means that for each connected regions, we compare the overlap ratios and treat, no matter it's large or small, treat each regions as an independent one, equivalent. And this way, we got 2 different evaluations. And also, we also consider the hardware support. So for example, in these figures, in this benchmark, the different volume of the dot corresponds to memory requirement for each data set. And x-axis corresponds to inference time, and the y-axis corresponds to accuracy. So in general, this figure gives a very comprehensive information about the methods. So this is the result. I think it's too small and it doesn't matter. It's just the previous methods. And this is the localization performance. As you can see that in terms of the numerical result, generally across all 5 or 6 benchmark, the patch count is good. Reverse distillation is okay. But none of them outperforms others. Regarding the segmentation performance, reverse distillation is okay. but rest of them, some of them is not that good for localizations. And in sum, it's just a benchmark. Comprehensive and standardized benchmark includes 6 benchmarks from 5 common medical domain and well-structured code base for use. And we try to maintain it to include more data set and more algorithms for future use. And the paper or the benchmark also provide in-depth discussion or analysis. So welcome to use that one. Hopefully it helps. Thank you.
Thank you very much. I think since we are a bit tight on time, I think we might have time for one question, if there's any. Yeah.
So in general, when you cope with medical data, you have the variability due to the acquisition system that is injecting some noise variability. So how to cope with that variability and understand that is not abnormal, but is just due to the acquisition system?
Okay, it's a very nice question. Actually, I can show you one example to answer your question. So for example, for this liver. So for liver images, we know that it's low contrast. And when we enhance the performance, it's a lot of noise. So for this purpose, we think that we probably try to keep the original morphology in also includes the noise, because the noise coming from the image modality, when we have imaging, we cannot avoid that. So we include this noise in the data set. Hopefully the model can know that, for example, this pixel image or the pixel noise, for example, coming from the image modality. But for the data set, we also provide a second version. The second version means that here we say that we do the histogram enhancement. So you can see there are a lot of images. The original low contrast, the original image data set actually are less noisy, but less contrast, but we also provide that copy of the data set. So I think sometimes maybe different researchers may need to consider that one. So we also provide access to that original query data set instead of this pre-processed one. So we will relax this usability for the researchers instead of us, because we are not physicians. Actually, it's very hard to determine to use it or not use it. Yeah, thank you.
All right, then thanks again. And next up, we have one more paper presentation from Shang Hong about the text-align anomaly detection backbone.
Hello, everyone. It's my pleasure to present this paper, test align alarming backbone model for industrial inspection task. So this is a joint work with my student. He already graduated earlier this year, and Ho Wen Lee, and we are from National Tsinghua University in Taiwan. Okay, so this work is mainly focused on industrial applications, and especially anomaly detection, localization, and also some defect classification. And we in this work we mainly focus on proposing the better pre-trained backbone, which is more suitable for the industrial inspection task. And I'll give some more detailed reason why this is important for the industrial applications. And by using this pre-trained backbone for this industrial application, we can improve the performance of some existing anomaly detection and also the defect classification work. Okay, and this is this figure gives some rough idea of the existing method, well, the conventional anomaly detection model, which lots of existing method use some pre-trained model, like ImageNet pre-trained model is very popularly used. But they may not be very suitable. I will give more detailed reason in the next slide. And here we want to use also the visual language model with only use a text encoder to guide training for a better, more suitable pre-trained model for the industrial application. Okay, so this is a feature embedded distribution. So hopefully, if we have this text aligned as guidance for the pre-trained model training, and then we can have better separation of normal and abnormal. If a conventional method, they may be mixed together. So this, by using this more suitable pre-trained model, the anomaly detection could be performance can be improved. So the issue with existing method is we have each task usually have one model. So if you have n task, you will have a model which is not very critical. Okay, so of course, if you have like a zero shot, then you don't need to have just have one model for all the different tasks. That would be ideal. Okay. And also, lots of methods use ImageNet as a pre-trained model. Yes, but there's a large domain gap between the ImageNet and also the industrial data. Okay, so in this we want to address this problem. Okay, because ImageNet, the pre-trained model, they use a classification of different classes, and this global content or global feature extracted from image may not be used very suitable for detecting local or subtle anomalies. Okay, so here, this is our proposed framework. So we propose to a pre-trained model, which is suitable for the industrial task, and we will generate anomalies. Okay, by like NSA method, which is a synthetic anomaly generator, and we found the normal image, and then the upper one is found the text encoder, which here in this work we use a clip text encoder. Okay, and similar to the clip, we want to align the image embedding with the text embedding. Okay. And here we will focus on normal, on abnormal, and also for many different types of industrial object class, including structure object class and also structural texture classes. Okay. So this is our main idea of how this anomaly text aware pre-training strategy. So more detail, like in the synthetic anomaly samples, we use, as I mentioned earlier, we use NSA, and here the comparison of different anomaly synthetic method, and we think NSA turns out to provide a better result, especially is more provide more natural looking anomaly. And for the text prompt, we use several different prompts for each class and to describe the anomaly, and also for each class and with different anomaly, we will collect several different prompts, and finally we will do an averaging of the testing embedding for all these prompts. Okay, and here is the training detail. As I mentioned earlier, we have used many object types, and also the normal and abnormal classes, and for each class we will have different prompts and then computer average. So this is similar to the clip training method. Is here this by using this matrix compute the cosine similarity between the image embedding and the text embedding. But if in this work we only fix the text embedding, we only train the image embedding. Okay, here, and what we use the CNN model. Okay, here to train the image embedding such that it try to align with the text embedding, the corresponding text embedding. Okay, so here are the data set we use, or most of the data we use is a public data set like MVTech AD, BTAD, KSD, B2, and here skip. And also we use one wafer data set, wafer map data set for the defect classification experiment. Okay, so here are the experiment. We compare with the ImageNet, the pre-trained model, and TAB, our method, and test on different anomaly detection method, including RTIM, RD, 480, SimpleNet, RegNet, RegAD, and so on. Okay, and we test on ResNet 18 and ResNet 50. We can achieve consistent improvement, okay, on the anomaly detection. Okay, but for anomaly localization, there are some cases may not have better improvement, but is similar compared to the ImageNet. But note that ImageNet use millions of image for free training. Here we only use here just thousands of image to pre-train the model. So if we use a larger data set, the improvement will be much better. Here are some visualization of the anomaly localization compared with ImageNet pre-trained model. This is on RD480. This is input image. This is the anomaly localization by using ImageNet pre-trained model. This is by using our method. And of course, in some cases, our method can provide much better localization result compared to this ImageNet pre-trained. And this is a cross data set testing also on different data set, which is unrelated to VTech. And here again, the anomaly detection is much better, and localization sometimes may not be better, just some, but most of the case we still can improve the result. And this is a result on the wafer map, and there are many different kind of wafer defect. This is to do the defect classification. And here we want to visualize the embedding. This is before the fine tune is in the upper. Okay, so by using that, the left on the ImageNet pre-train, and on my right is the our pre-trained model. So our pre-trained model can have better separation of different defect types. Okay, and in the bottom is after pre-training, after fine-tuning. Okay, if finding we can even better. So the accuracy is also better compared to the ImageNet prediction model. Is like 3% improvement in the defect classification. So in conclusion, we propose this tab text align alarming backbone, which is a pre-training framework that train a backbone that's suitable for industrial inspection task. And we demonstrate superior performance on several anomaly detection, localization tests, and also on this defect classification task for industrial applications. Okay, thank you for your attention.
All right. Thank you very much. I'm not sure if we have any questions. Yeah, maybe one quick one.
Yeah, there seems to be some sort of a check path. I don't comment. It looks like a checkerboard, like.
I think this is related to the anomaly detection method. They probably is, I'm not very sure. I think so for your question, but yeah, that's yeah, we didn't look into this part. Yeah, I think yeah.
Okay, then yeah, thanks again. And okay, then we are gonna have our lunch break now. I believe we are meeting back here around 1:10, if I'm correct.
No, it's 5:05 p.m. We restarted. We also updated the schedule on the webpage, but actually for the afternoon, nothing changed. Yeah, so we'll start with a keynote and then with the whole challenge session that Paul and Samit will moderate then. Oh yeah, that's a good question. Yeah, so.
Well, we came here yesterday, so I mean, at 1:30 in the night, I was fresh. So I don't know how the day progresses, what's going to happen. But you're right today or Saturday? Oh, Saturday. It's yeah. Okay, so give me yeah. How long is it?
So, well, I have quite a lot of doing, so I've chosen about 30 hours. So I went from Sevilla to Vienna, Toronto, wow, so it was about 15 hours of flight. There are some, but they were too expensive. But I'm here on Thailand, and I think it's longer. I mean, even there are some that are quicker,
even then it takes like the lowest I've seen 4 hours. So I would say it's a bit problematic because our airport is so small and there are connections like work, so you can't really avoid studies. Sometimes.
Yeah, we turned it off. No.
It could
Check your slides.
Okay. Well, that mic's been absolutely fine.
I didn't want to find my schedule to the one here, so I have to do something and it was I couldn't focus anymore. Well, so the first thing I had to do was I mean, I could have just finished, but I had to check the callbacks and how because it makes workspace like the one day. So I had to change that to all the ones. But other than that, the pipeline pretty much I just checked one thing because the state method so I had to somehow add the fan from the run, so I just passed that through. I returned couple and then removed that state method. So
Check 2 2 2 2 2 2.
But look.
Okay, well, I hope you had a great lunch break and you're back here full of energy. So yeah, we will start with keynote speaker, Professor Radu Tudor Ionescu. He's from the University of Bucharest, from Romania, and his research background, I would say, is quite diverse. Actually, he has done a lot of different things, working on machine learning, computer vision, medical imaging, text mining, and so on and so forth. Quite impressive CV, I would say. So thanks for being here and giving a talk. And yeah, he will talk about video anomaly detection in real time. So looking very much forward to your talk.
Thank you for the presentation and thank you for the invitation to speak at this workshop. So today I'm going to present the recent results from our research group on video anomaly detection. The video anomaly detection task is known to be very challenging. As in images, you have the appearance of objects, but in video, you also have to take into account the motion. And the definition of abnormal event depends on context. So I provide two examples to illustrate this. We have the same action, a truck driving, but if it's driving on street, that is counted as normal. If it's driving in a pedestrian area, that's counted as abnormal. Another example is person running. If it's happening in a park or a court, that's again fine. If it's running from outside the bank, that's likely suspicious or abnormal. So because of this dependence on context, it is hard to collect abnormal example for training. So typically supervised learning methods are ruled out. But the main hypothesis that most works rely on is that abnormals are rare events, and we can just collect video, and most of that video is normal, and we can train our model on this video and formalize the task as outlier detection. But still, learning is hard without full supervision and abnormal training data, so there are methods that try to use or to introduce pseudo anomalies to obtain better results. Okay, so the current approaches in video anomaly detection can be divided in two main categories. We have the object-centric models that were introduced around 2019. They rely on a pre-trained object detector, and they obtain really good results because they eliminate a lot of the false positives. But because of this object detector, they can run at around 10 to 15 FPS. And we also have cube level methods that use spatial temporal cubes or take the whole frame as input. These models have typically lower performance because they can have some false positives around the video frames, but they can process the video a bit faster. So some of the methods can even reach over 100 FPS. But the problem is in the real world, for example, if we want to monitor an entire city, we have hundreds or thousands of cameras that need to be, the streams from these cameras need to be processed. And the current methods can process like 1 or 4 video streams at around 25 FPS, which is the normal frame rate for a video on a single GPU. So this is not scalable. We need more efficient methods. So this is the topic for today. In our past years, we try to develop more efficient methods that are scalable to this real world scenario. Okay, so we have developed two methods. One is still under review at Computer Vision and Image Understanding, and the other paper was accepted at the CVPR this year. So I'm going to present these two papers in the orders that I listed them. Okay, so the first work was done in collaboration with Fahad Shahbaz Khan from the MBZ UI University and also Professor Mubarak Shah from University of Central Florida. The goal of this work was to train a very fast frame level model and distill the knowledge from state-of-the-art object-centric models that use the pre-trained anomaly detectors. And our approach was to use standard and adversarial distillation jointly and apply this at multiple resolutions. As teacher models, we used two of the state-of-the-art models that we was also developed by our group in previous years. They are based on this pre-trained object detectors. They can process one video in real time, but they're not scalable. Okay, so the first stage of training is to do train an autoencoder for the classic reconstruction task that is commonly used in abnormal event detection. We use temporal sequences of 3 video frames that are given as input to a convolutional transformer architecture. This is a very lightweight architecture that has about 0.8 G-flops and around 5-6 million parameters. So the first part is pretty standard. We just want to reconstruct the middle frame. And in the second training stage, we perform the knowledge distillation from the teachers. So the training video is passed to the teacher models, which use a pre-trained object detector. These gives us some bounding box for the objects. These objects are used to as input for the object-centric anomaly models, and they give us some anomaly maps at the frame level. So basically, we can take the bounding box locations with the assigned anomaly score and reconstruct the anomaly map for a video frame that looks something like this. So these anomaly maps are distilled into our student model. Now, the student doesn't do any object detection, so it's a frame level method. It takes the whole frame as input and tries to reproduce these anomaly maps from the teacher models. So we have for the standard distillation, we use a max pooling operation to reduce the anomaly maps. We empirically observed that this produces better performance. We use a max pooling to reduce the size of the original anomaly maps. And then we perform the knowledge distillation with respect to the output of the student. And for the adversarial distillation, we introduce 2 discriminator architectures. There is one for each teacher model, and these are supposed to discriminate between the data or the anomaly maps that are generated by the teachers and the anomaly map generated by the student. So as the discriminators perform well on this task, it means that the student is not able to really copy the teacher models. Okay, so this is the whole architecture. So I mentioned earlier that is multi-scale. So actually, from the original autoencoder, we remove the decoder part and replace this with some multi-scale downsampling blocks that use convolutions, and they downscale at different resolutions. So for each resolution of the anomaly map, we apply the knowledge distillation, and the adversarial knowledge distillation is applied on the a discriminator that combines all the resolutions into one architecture through the concatenation operation. We tested this architecture on publicly available data sets that are commonly used for video anomaly detection, and we used the frame level AOC and also the evaluation criteria that looks at localization performance, such as RBDC and TBDC. In terms of the output resolution, we observed better results if we use a lower resolution, and also better results if we combine multiple resolutions into a single architecture. Then we tried to see the effect of different loss functions, and we found that the combination of all three works best. The adversarial distillation has a mode collapse if we use it alone, but if we combine it with the knowledge distillation and also the autoencoder pre-training, leads to performance improvements. Okay, we also have done some ablation on the number of teachers and the type of teachers. So this essentially using more teachers leads to better results. And also we considered different architectures for the adversarial training part, where we try to use only one discriminator for both teachers and one output branch for the student, a single output branch for both teachers, or separate output branches in the student for each independent teacher. It seems that the architecture that we presented with two discriminators and one output from the student works best. Yeah, and also the diversity of teachers has some role in this. So if we use the same teacher twice, we get slightly lower results. And if we use three teachers, we get improved performance, but it's also a trade-off in terms of training time. Here we have a comparison with different results from the literature. We have separated object-centric and frame-level methods. And in terms, when we compare with similar architectures based on frame or cube-level features, we obtain pretty good results, but you observe that the frame rate is much better than the other approaches. We also have the region and track level evaluation, where we obtain better results than other frame level or cube level methods. And to put things into perspective, if we compare the performance versus the frame rate, our method stands here at the far right in these figures. So the performance is likely kind of average in terms of comparison with the recent state-of-the-art methods, but the method is much faster. If we look at some qualitative results, we see that interestingly, our student detects anomalies where the object detectors fails. So we have the second column where the teachers that rely on pre-trained object detector do not detect these papers that are thrown in the air. But we see that for this region, our student model has detected the papers, which is a interesting outcome of the method. Okay, here we have some frame level scores, where again we observe that our student can sometimes surpass both teacher models. And to conclude this paper, we obtained outstanding inference time. The idea of doing standard and adversarial distillation at multiple resolution is useful, but there are some disadvantages. So in this method, while the inference time is really fast, we still need some teachers during training. So and we don't use only one teacher, we use two of them. So the training is actually slower than just training one teacher, right? So the training time is actually slower for this architecture, and the performance is kind of average, is not excellent. We wanted to obtain better performance. So the question is if we can keep the inference speed of this architecture and try to alleviate these disadvantages to make sure that the training time is also fast, and we also get somewhat better results. And these things are addressed in the next paper that was accepted at CVPR. So this is done in collaboration with the same people as before. I think just a minor modification in terms of authors. Okay, so we use the masked autoencoder architecture. Actually, we do not use a VIT. We use the convolutional vision transformer as in the previous architecture. But because we mask tokens, this architecture is, this model is even faster. So you will see that the inference time is actually better than the previous approach. And we also completely changed the training of the architecture to get improved performance. Okay, so we do a self-distillation training pipeline. So we don't use these pre-trained or external teachers. We use self-distillation, and we also leverage the discrepancy between the teacher output and student output to boost accuracy. We also perform a data augmentation based on synthetic anomalies, which enables us to introduce some supervision. So we use a cross-entropy loss in the architecture. Okay, so for the masked autoencoder framework, the things are typically done randomly. The tokens are masked randomly, but this is suboptimal in video anomaly detection because most of the background scenes are static and it's not interesting or useful to learn to reconstruct the background scene. We aim to reconstruct the objects that are moving in the scene. So we introduced this motion gradient weighting. We actually do still use the random token masking, but in the loss function, we weight the tokens such that those that contain higher motion, they receive a higher weight. So in order to compute these weights, we compute the gradient map of consecutive video frames. We divide the gradient map into tokens to match the size of the original image tokens. And for each these gradient patches, let's say, we compute the maximum gradient magnitude per channel and then compute the average over the channels. And then we normalize and we obtain a single weight for each of these tokens that is proportional to the motion magnitude in each gradient patch. So we will use this mask to weight in the loss function the reconstruction of the tokens. Okay, so we have the here with W the weights that correspond to our tokens. E are the patches from the original frame. P hat are the reconstructed tokens, and our loss function looks something like this. So we use the mean square error reconstruction that is weighted with this motion gradient weights. The pipeline looks like this. So we have the training data. We mask some tokens randomly. We pass them through the autoencoder, masked autoencoder. We have the predicted frame, and then we have another branch that estimates the motion of tokens. And then we weight the tokens in the reconstruction loss with respect to these to the detected motion. Okay, the second thing that we do is augment the training data. So we use examples from this abnormal data set that was introduced at CVPR 2022 that has virtual scenes. And we randomly introduce objects in the scene that simulate anomalies. So this video is just to give you an idea of how they look. And next, what we do with the synthetic data is we do actually several things. So the first part is we try to reconstruct the input, the RGB input, but without the introduced anomaly. So we have a synthetic anomaly that is added in the video frame, but in the output, we want to reconstruct the frame without the respective anomaly. So this creates a high reconstruction error for anomalies. We also have an anomaly map. So now we can introduce and ask the model to produce some anomaly maps. And in the anomaly maps, we can use, so basically we have, before introducing synthetic anomalies, the anomaly maps would be just black. So there were no anomalies. Now with the synthetic anomalies, the model can also learn to segment these anomalies. And additionally, we can also use this to train a classification head with cross entropy loss. Okay, and we also have the self-distillation. So we introduce another lightweight decoder into the architecture, that is the student. When we train the student, the other part of the architecture, the teacher and the classification head, are frozen, and the student aims to reproduce the output of the teacher. Okay. And in this distillation, we also use the same motion gradient weights as before. Finally, during inference, the anomaly score is basically a weighted combination of the output from all these heads, the teacher head, the student head, and the classification head. Okay, so to show some ablation results. So when we introduce the first line here is just the typical masked autoencoder framework that already obtains fairly good results without significant changes. When we introduce the self-distillation and the motion gradients, we get better results. Then we introduce the synthetic data, which by itself doesn't add too much to the architecture, but without the synthetic data, using the anomaly maps and the classification head wouldn't have been possible. So actually, if we count the final performance, we see that the synthetic data is really useful for our model. Here we compare with frame level or cube level methods. And in red, we have the top scores of these methods. And we see that most of them are for our architecture on these 4 data sets. And when we compare with object-centric methods, our method is not still below, but it's still close to these object-centric methods. We also get better results in terms of region and track level scores. And we see that our method now obtains better frame level AUC scores and even faster FPS rates. We can analyze the qualitative results and see that our model is able to localize anomalies quite well. So these are the anomaly maps from the teacher and student decoders in our architecture. And this is the teacher-student discrepancy that we also use in the architecture, and this is the ground truth. So we see that the model generally correlates well with the ground truth. We can also see that the predicted frames that should I continue or just wait for? Is this the new mic? Okay. Yeah, so we can also look at the predicted frames and see that our architecture tends to remove the anomalies from the video frame. So we see this person on a bicycle that is almost completely removed from the scene by the student decoder. Okay, and we have some videos to show here, but I need to switch, right? Okay, so we have some example videos for this framework. So below we have the anomaly score at the frame level. In pink, we have the ground truth anomaly events. And in the middle, you will see the anomaly map. And when the person runs, this is an abnormal event, and our model shows that in the anomaly map. So this is a video from the Avenue dataset, and I think we have another example. Is it playing out automatically? Okay, then just leave it until the end. Yeah, okay. Okay, so I'm going back to the slides. Here. Slideshow. So, okay, we had the videos played. And now for the conclusions. So this method, again, reaches outstanding inference time. It has a performance that is very close to the state-of-the-art object-centric methods and obtains a very good trade-off between speed and accuracy. So this research was done in collaboration with my PhD students, Alin and Katalin. As I mentioned, also with our collaborators, Fahad Khan and Mubarak Shah. And I thank you for your time. And we maybe have still time for questions. Okay.
Yes, so thank you very much for the interesting talk. In case there are any questions, just walk up to the microphone and ask them.
Thank you for the talk. So I think if I catch earlier in the beginning, you said that current algorithms are limited like in some frame rate, and you want to push this frame rate to be faster, right?
Yeah.
So what would be like a sufficient fair frame rate? Which kind of application need like a much higher frame rate?
So yeah, maybe there is no limit in terms of the frame rate, but with the frame rate that we have now, you can process, I think, like 50 video streams or more on one GPU. So this is, I think, scalable for today's standards.
Okay, and do you know of any application that need like extremely faster frame rate, like?
And even faster than this, or?
Yeah, I'm asking you.
No, so basically this research was motivated also by our, we collaborated with a company, and basically this request came from their side. So we tried to deploy this previous model that we developed in real scenarios, but they figured out, okay, the costs to run this model is too high, and we can run maybe on a few cameras, but not on the entire city. So they wanted to run the model on tens or hundreds of cameras. So this model is able to do that now.
Okay, thank you.
Okay, you're welcome.
So in contrast to a lot of the anomaly detection work that we saw this morning, looking at maybe image samples, here you're very reliant, it appears, on ground truth labeled data. Do you see a way forward where you'd move away from that reliance in future research?
You mean at test time, or?
I guess at training time, so you'd rely less on labeled ground truth data.
So on training data is still using only normal videos.
Okay.
We use that synthetic anomalies to introduce labels into the training. But the anomalies that we introduce are kind of out of distribution, and we use the same anomalies for all the data sets, or real data sets that we used without trying to do any changes or specific things. So I think the model is pretty generic in that sense.
Okay, thank you.
But yeah, I think even if the framework is that you typically use unlabeled videos that contain mostly normal events, some way of introducing supervision is always helpful, but you have to make sure that we introduce or use the supervision in a way that doesn't make the model too specific to the data set. Still keep its generalization capacity.
Okay, thank you. Very good. Thank you.
Yeah, so thanks again for the really nice talk. We make a short break of about like 5 minutes. We'll prepare everything for the challenge, and then we'll meet again here. So you can grab something to drink, and then, yeah, we continue.
gosh, yes. Babar, are you ready? So we will talk in 20 minutes and then you will jump.
Sure.
He's talking, but I cannot.
Hi, I'm there. Hello.
Can you speak again, Babar?
Hi, I'm speaking. Yes. Can you
Okay.
like hear me?
Yes, thank you. All good. Just technical check. Thank you.
So stupid from my side.
Hello, everyone. Thank you for stay here with us.
We know this is, the last part of the workshop. It's great to have all this conversation with all the anomaly detection leaders. And we have the opportunity this year to sponsor the challenge. Basically, in this challenge, we have 2 categories, and we were inviting developers to create, put their knowledge in these challenges. So we will explain in this overview what categories we were working with. But I want to, first of all, I want to say thank you to the organizers, because this was a great opportunity to work together and working together in the field. And right now, after watching all these presentations, we will see more things coming the next years, for sure. And I think that it's also this opportunity is great to say thank you to the Anomaly team, because they take the responsibility to evaluate all the submissions that we receive. So we have more than 420 participants in the challenge. That is a huge number. We receive around 100 submissions. And finally, eligible, we have around 60 submissions, 60 submissions. And the evaluation was hard. And I really want to say thank you to all the people that was involved in this work. So today we will have Dick. He will explain us how this challenge worked, and the evaluation process, data sets, and also explain what the challenge means. We started this challenge in April, and in April 15. And the submissions, we received the submissions until June 7th, June 1st, sorry. And we have just 1 week to review all the submissions. That was, a challenge as well, just review the submissions. So I hope that you can enjoy this overview. And next year, I want to see you making these submissions in this challenge for the next year. So over to me, Dick. Thank you.
Hello, everyone. My name is Dick Amel. I'm a research engineer at Intel. And this year, together with my team, we had the honor of organizing the Visual Anomaly Detection Challenge for this workshop. So at Intel, we see a lot of different industrial visual inspection use cases, which we aim to address with anomaly detection techniques. And in these real world kind of industrial inspection use cases, we sometimes see that the requirements there are a little bit different from what we tend to focus on in research. And this is what inspired us to design these 2 categories of the challenge for this year. So the first category was adapt and detect robust anomaly detection in real-world applications. And the second category was VLM anomaly challenge, few-shot learning for logical and structural detection. So let's jump into the details. So to introduce the first challenge, let's have a look at this simplified data set. I'm sure this is familiar for everyone. Yeah, naturally, we're trying to detect defects here. So it's quite straightforward, right? Top right image has a defect, and the bottom middle image has a defect. So it's quite straightforward to train a model on this data set. We train on the normal images. We do inference on the test images, and we detect the defects. We can make the data set a little bit bigger. Still, it's quite straightforward, right? It's easy to see which images are anomalous. But now let's imagine that we train our model on this data set. Then we deploy our model. And once our model is deployed, the images may look a bit more like this. So what we're seeing here is maybe some different lighting conditions, maybe some noisy images, some changes in the camera position, in the camera angle. In this case, will our model still be able to nicely detect the anomalies, or are we going to see some false positives? Now, this problem is what inspired the first track of the category, and this is a problem that we refer to as domain drift. So essentially, this means that the distribution of the data, so even the distribution of the normal images, may be different at inference time than the distribution of the normal images that we trained on during training time. So to capture this in a challenge category, we designed the adapt and detect category. So adapt and detect robust anomaly detection in real-world applications, where the aim was to develop anomaly detection models that demonstrate some sort of robustness against these external factors, against these this variability in the data. So what we were looking for here is one-class learning approaches, where we train on normal images, and we do inference on a set of images that has a slightly different data distribution than the training set. So to achieve this, we created a new data set. This data set was based on the MVTech data set. I'm sure everyone is familiar with the MVTech anomaly detection data set. And what we did is we applied some data augmentations to the test set of this data set. And these augmentations were chosen in such a way that they simulate the kind of real-world domain shift that we can see. So I'll show you the list of transforms that we used. So the first type of domain shift that we wanted to simulate is motion camera or like changes, differences in the motion, the camera quality. So we introduced Gaussian blur. We introduced Gaussian noise. The second type of domain shift was lighting conditions. For this, we introduced random brightness changes, random contrast changes, and random saturation changes, random shadow as well. And the last type of domain shift was camera position. So for this, we introduced random rotations, random translations, and random perspective transforms. So these were the different transforms that we applied to the test images of the MVTech dataset to obtain our new evaluation set for this challenge. So to obtain the final dataset, we applied these augmentations at random to the test set. So for each image in the test set, we chose either a single type of domain shift or two types of domain shift randomly. And then for each selected type of domain shift, we randomly sampled one single transform. So using this approach, we created 3 different versions of the dataset with different random seeds to ensure variability. And yeah, the result is what we see on the right. So these are some samples from the final dataset, which are basically the test images of MVTech with the random augmentations applied to them. We will release the code of generating the dataset so that everyone can reproduce it, and also to stimulate further research in this area. So to evaluate the submissions, we required each of the participants to submit a Python module that implements their model and the pre-trained weights for each of the 15 categories of the MVTech dataset. We use the models to predict the image level and pixel level anomaly scores. And we use these anomaly scores to obtain the F1 max score, which is essentially the maximum F1 score that you can achieve based on the raw anomaly score predictions by varying the threshold. So we obtained the F1 max score for each of the 15 categories and each of the 3 different versions of the dataset. And we took the average. And then the final evaluation score for each submission was the harmonic mean of the image level and the pixel level scores. So let's move on to the second category. So to introduce this category of the challenge, let's have a look at this example. So this is a normal image that we're looking at. So what do we see here? We see a zip bag which contains 2 nuts, 2 washers, and 2 bolts, of which one screws, sorry, of which one is a short screw and the other one is a long screw. Now let's have a look at some anomalous examples. So where are the defects in these images? So on the left-hand side, we see that the short screw has been replaced by a long screw. And on the right-hand side, we see that the head of the short screw is broken. So these are kind of 2 different types of anomaly, right? So on the one hand, we have a change in the composition of the contents of the zip bag, while on the other side, we have a broken component, which is more like a structural integrity. So the first one is what we like to call logical anomalies, and the right one is what we like to call structural anomalies. And what we tend to see in industry is that the current state-of-the-art models are quite good at recognizing the structural anomalies, but for logical anomalies, they're struggling. And we feel that with the recent surge in language-guided models, this might change. So this was the scope of the second challenge. So the name of the second challenge, VLM Anomaly Challenge, Few-Shot Learning for Logical and Structural Detection. So the idea here was to develop few-shot learning models that use vision language models to find structural and logical anomalies in the data set. So for the data set, we use the MVTech Logical Constraints dataset, or MVTech Loco. The example with the screwback is one of the 5 categories of this dataset, but there are 4 other categories as well. In total, there are over 1,500 test images covering 561 logical anomalies and 432 structural anomalies. So for the evaluation, again, participants were required to submit a Python module implementing their class. Optionally, if needed, they could provide pre-trained weights. And then we ran this model in a few-shot fashion while varying the number of K reference images between 1, 2, 4, and 8. And for each setting of K, we repeated the experiment 3 times with a different selection of random reference images. So for each of the 3 runs, we averaged the F1 max score. And finally, the effectiveness of the algorithm was evaluated by plotting these F1 max values against the K-shot values and taking the area under the curve. So this is the area under the F1 max curve, or AUFC. This is the submission platform that we used to gather the submissions of the participants. So before we show the leaderboard, let's have a quick look at some details of the numbers of submissions. Paula already mentioned it. So for category 1, we had a total of 37 submissions of 24 different teams. Unfortunately, we had to disqualify some of the participants due to, for example, missing report or missing code or missing weights. And we had to also reject some submissions because they failed to run because there was a problem with their model implementation. So similarly for category 2, we had a total of 26 submissions across 18 teams, of which 11 were qualified and 10 different teams. So let's have a look at the final leaderboards. So for category 1, I would like to congratulate Babar Hussein with his submission ARNet for robust anomaly detection. Second place was for team IAIR. And honorable mentions for the runner-ups, Amal Al-Salami and his team, and Yukino Suzuki with his ensemble patch score. So for the second category, Team Cassia IVA won first prize with Anomaly MOE, and second prize was for Nestor Bau with RJ Voyager's submission. And the honorable mention for the runner-ups were the Loco project and MVTech Loco Diffusion AD. These are the prizes for the winners. So first prize for each category received the newest Intel AI PC, which is a laptop for on-the-go boosting AI performance. And the second prize was an Intel Discrete Arc GPU. And both the first prize and second prize winners were invited to present their solutions during today's workshop, either live or by sending in a video. So here are the certificates. Again, congratulations to all the winners. I think right now we're going to go live to the winner of the first category. Oh, this first? Oh, yeah. So first, second place? Oh, sorry. Okay. Yeah.
Hello, everyone. I'm Tan Weitang from the Institute of Artificial Intelligence and Robotics at Xi'an Jiaotong University in Xi'an, China. It's my honor to present our solution, generalized novelty learning for robust anomaly detection for the CVPR 2024 VAND 2.0 Challenge Category 1. Industry anomaly detection is a crucial task that focuses on detecting and localizing anomalies in images of industrial products. The diversity of anomaly samples poses a challenge, leading to the difficult approach of treating anomaly detection as an unsupervised program that relies solely on normal samples for training. By capturing and modeling the distribution of normal patterns, subsequent anomaly detection can be achieved by identifying deviations from the learned distribution. Let's briefly review Category 1 of the VAND 2.0 challenge. Adapt and detect robust anomaly detection in real-world application. Real-world scenarios involves omissions caused by the camera noise or low light conditions, variations in brightness due to different times of the day, and the transformations caused by camera positions. However, most existing methods often struggle with robustness in these real-world scenarios. Their limitation lies in their ability to only learn the novelty of in-distribution training data. While some out-of-distribution novel data may be incorrectly classified as anomalies, we aim for our network to then generalize the novelty. When the decision boundary is flexible enough to classify both in-distribution and out-of-distribution novel data as novel, while identifying anomalies as anomalies. To achieve this goal, a basic idea is to simulate out-of-distribution novel data through data implementations during training, allowing the network to learn a large variety of normal data distributions. However, this approach raises two questions. First, does the model have the ability to memorize the substantial augmented number data without increasing model size? Second, whether learned novel boundary become too generalized, leading to undesired generalization to anomalies. With these questions in mind, we conducted our method exploration. Firstly, we choose reverse distillation as our baseline, which trains knowledge distillation between an imaginary pre-trained teacher encoder and a learnable student encoder. It can be seen as a multi-scale feature reconstruction. Due to its compact embedding and non-similarity structure, it can effectively avoid the reconstruction of anomalies. To enhance the recall of out-of-distribution novelty, we first improved the reverse distillation framework to learn a generalized novelty boundary. Firstly, we use data augmentation during training to simulate all the normal data and train the student encoder to fit the diverse augmented normal patterns. Secondly, we adopted a hard distillation loss and a structure distillation loss to enhance capacity for recording novelty. For data augmentation, our augmentation methods included the use of single or combinations of Gaussian noise, brightness changes, and rotation, and so on. Here are some examples. As for the loss, the original loss only constrained the increased similarity of touch-wise features between the student and the teacher. We introduced a structure loss that considers the similarity between patches. Our insight is that the distribution shifts typically only change the overall appearance of the image, while the similarity between patches remains relatively unchanged. On the other hand, the presence of anomalies can disrupt the relationships between patches. Additionally, we adopted a hard knowledge distillation loss to enhance the distillation of specific fine-grained normal textures and rare normal patterns. To improve the accuracy of anomaly localization, we incorporated a segmentation subnetwork to integrate the outputs of the teacher and student models. To enable the network to handle all the anomalies, we first synthesized anomalies by adding turning noise and external textures to normal data, and then used the mentioned data augmentation techniques to simulate distribution shifts. Finally, we achieved second place in the VAND 2.0 challenge category 1 with a 94.7% image level F1 max score and a 59.8% pixel level F1 max score. We believe that our retrained model will perform even better as we have fixed the bug related to rotation augmentation. We will update our rates on the platform accordingly. Additionally, our detection performance surpassed the 80 shift by 0.8% on their benchmark. Lastly, we would like to present our visualization results in various distribution shift scenarios. Our method not only detects out of the distribution anomalies, but also records out of the distribution normals and patches, effectively avoiding false positives. Thank you for listening. If you have any questions, please feel free to contact me via this email address.
All right, so I think that sums it up for the number 2 of the first category. We'll now go live to the winners of this category. works.
Hi, can I share my screen for this?
Yes, just go ahead, Jules. Yeah, we can see it. So I think you can already start.
Okay, okay, thank you very much. Okay, so I'll start now. Hi, this is Babar from TCL Corporate Research Hong Kong. And I'm going to present to you our work ARNet for Robust Anomaly Detection, a winner for the VAND 2.0 Category 1 challenge. And my colleague are Chiang Liu and Daha Yu, also from the TCL Corporate Research Hong Kong. So first overview of the challenge, I think we have already seen it in the workshop introduction. The challenge is to design an anomaly detection and segmentation model that can adapt to unknown real-world variations, which could include lighting variations, camera noise, different angles. And these variations were not known to us exactly how he showed us in the table during the competition. So we have to make a guess on what kind of real-world anomalies, or the augmentations can happen during the test time. And the data set used was MVTech 80. And we were to train using the one-class training paradigm, which means only the normal images can be used for training. And the evaluation metric was F1 max score for image and pixel level prediction. And we take a mean of all the categories for both image and pixel level, and that will become the final score. So first, let me start by the selection approach. We have a very simple approach. We first investigate the top performing architectures on the MVTech 80 benchmark. And then we compare their performance under the augmented test set. And then we see which architecture has the most promising performance and also other benefits that we can pick. So as you can see here, we have 3 architectures, very popular architecture. I think most of you are already familiar with them. Student teacher base or efficient AD architecture, in which we distill a pre-trained teacher using normal images onto a student. And it's very memory and compute efficient architecture. And then in the second, you can see we go with the feature memory bank for the patch core method, in which we use patch level features to form a memory bank and to do the anomaly detection on the test images. It has a very good image level detection performance. And the reconstruction-based network, which uses synthetic anomalies to reconstruct anomalous features to detect the defects. And that one, I think, has slightly better segmentation performance. So we tested these 3 architectures for 4 most challenging categories. In order to save time and compute, we picked the 4 most challenging categories, which are cable, capsule, pill, and screw. And we apply the augmentations on the training set, and we train all of these on the same data set and evaluate on the same augmented version of the test set. And we find that the ARNet, or the reconstruction-based method, actually outperformed the other 2. And we also select this architecture on the reason that because using the synthetic anomaly, it makes the training to be in somewhat supervised. And that helps the model focus on the boundaries of the anomaly as well as the background. Yeah. Yeah. And then for the real world variations, how we try to simulate the real world variation using data augmentation based on what
sorry, Baba, could you maybe restart the slide, because we couldn't hear you? We had some audio problems in the room.
Okay, sorry.
Yeah, exactly. Yeah, just not from the very beginning, just kind of the last slide you were talking about. I think we missed like 30 seconds or so.
This one. Okay. Yeah. Thank you for letting me know.
Yeah, so, the next one.
The next one, right?
Yes,
yeah.
Exactly.
Yeah. Okay. So for this one, what we do is that those 3 architectures, we evaluated them on the 4 most challenging categories of MVTech 80, which is cable, capsule, pill, and screw. And we trained these models on the augmented version of the training set, and then we evaluated on the augmented version of the test set. And we find that the RealNet or the reconstruction-based method outperform the other methods. And the other reason we select this RealNet architecture is because using the synthetic anomalies, we somewhat train the model in a supervised nature, which helps the model learn the boundaries of the defect versus the actual object. And that helps us increase the pixel level performance, which is a very important criteria for the evaluation. So here I go over the real-world variations of how we try to simulate these real-world variation using the data augmentations. So for brightness, for different times of day and lighting condition, we use the brightness augmentation. We use Gaussian blur for simulating the camera out of focus and Gaussian noise to simulate the sensor noise. We use RGB shift to simulate different camera models, how they reproduce RGB colors for the same image, and also rotation and translation to simulate different capturing angles. And here you see some examples of the screw category as well as the wood category of showing different augmentations. So most of the augmentations the model can handle very well, but we find that the most challenging one is the different camera angles. So here I show 4 examples. So on the top right, you can see the cable that is slightly shifted and rotated. And the introduction of the new pixel immediately confuses the model, as you can see here. And if we decided to, instead of filling in the black or 0 pixel, if you use the wraparound option for this augmentation, then the model also gets confused by this extra portion coming up due to wrapping around, and that confuses the model again. Same is true for this hazelnut category. And also we noticed that, for example, in this pill image, when the image is very closely shifted to the edge of the image, then the model will start to think that there is some kind of defect close to this edge. So all of these make us think that the most simple and robust solution for this would be if we can somehow make the model know where is exactly the foreground that it needs to detect, and then it can ignore completely what is happening in the background areas. That way we don't have to worry about during the evaluation what kind of background they're using, whether they're completely changing the background or whether they're using the same background, using the black pixel or using other pixel for filling. So this is the thing that we added on top of the original network. So first, let me describe to you the original architecture, and then I'll show what we add on top of it. So originally, using the synthetic images, we put them into the backbone to get the pre-trained features for the first 4 layers. And those go into this AFS or Anomaly Aware Feature Selector block to select the most relevant features for anomaly detection that go into this reconstruction network using UNets that tries to reconstruct the anomalous feature such that if you take the difference of these features before reconstruction and after reconstruction, you get these residuals which contain the information of the anomaly, which you can pass to this reconstruction residual selector or RRS module, which tries to do the max pooling and the average pooling to try to select the slices of the features which contains the anomalous feature, and then you apply some convolutional layers to get to the final anomaly mask. So we have 2 losses, reconstruction loss and the anomaly segmentation loss for this model. And then to add the foreground information, we added this foreground predictor branch and this residual reweighting. This foreground predictor branch actually takes in the first 3 layers of the features, and then we do this UNet kind of aggregation where we start from the lowest resolution feature, we upsample them, concatenate them, then the next layer, and then convolute them, and then we continue to do this until we aggregated all the features, and then we have finally the very accurate mask or the foreground mask for the image. And then we use this foreground mask to do the re-weighting of these residual using learnable weight factors before we feed them into the RRS discriminator. And that helps the model focus on the foreground areas. And now we have the foreground prediction loss as well. So the total loss for our model becomes the reconstruction, segmentation, as the foreground prediction loss. Now for this foreground prediction, we actually need the ground truth foreground mask too. For this, we use a very simple approach that we use the segment anything model from Meta to automatically generate the foreground of all the categories in one go. We use this approach that we have one image and then we select 4 corner points at the margin of 10 pixels from the corner, and then we use them to form a prompt that helps the SAM model predict where is the background area. We invert the mask, we apply some morphological operations to clean the mask, and we get a very good quality foreground mask, which you can see in this example here for a screw image. The mask originally generated by the RealNet using the simple thresholding scheme is not detailed at all, versus the one generated by SAM, you can see is very high quality. And now I come towards generating the synthetic training data. For this, we use the strength controllable diffusion anomaly synthesis, SDAS, that is proposed in the original RealNet. And it's shown here. So this diffusion model is basically, you see here, is trained on the normal images to learn the distribution of normal images. And then when we want to sample the anomaly image, we try to sample it from the low density areas, and that gives us this noisy version of the image. And then we also combine it with the describable texture dataset, or DTD, which is also used in a lot of other works for added performance boost. And also through experiment, we learned that if we use totally black pixel to represent synthetic anomaly, that also helps in the performance. So we randomly select one of these 3 options for having our synthetic anomaly. That synthetic image is cropped using this Perlin noise generator to crop this anomaly area. Then we put it on top of the normal image to get our synthetic anomaly image and apply augmentations to get our final training image. And for model training and evaluation, as I said, we use SDAS. We actually generate 256 images per class for using this synthetic data set. And then when we do the sampling, we have SDAS, DTD, and black defects. They are sampled at a probability of 45, 45, and 10% respectively. Here we show some examples of 3 different types of textures for hazelnut category and the cable category. And we use, for training, use a 3090 GPU with batch size of 16. We train for 1500 epochs with a small learning rate, you can see. We trained for 500 extra epochs than the original RealNet to accommodate for the augmentations. And for evaluation, we multiply the test set 3 times so that every image has seen 3 different augmentations. And the augmentation probability we use is about 85%. We use AUROC and F1 max for image and pixel level as the evaluation score. So here I show the results. So we compare the test set with no augmentations, that is the original MVTech, and then the test set with augmentation using the simulated real world augmentations. And I show the image and pixel level F1 max score for all categories. So overall mean, you can see that the image and pixel level score only very slightly drop when we go from no augmentations to with augmentation, which shows the robustness of the performance. One thing to notice is that the model still somewhat struggle for the cable, screw, and transistor categories, which is reflected by the relatively low scores. So there is room for improvement in these 3 categories, and I'll go to it later. And also we compare with the original RealNet. So in this measurement, you can see that although RealNet has a very good score for the image and pixel level for no augmentation, but once we go towards the augmented version of the test set, the performance significantly drop, versus the performance stays very stable for our proposed ARNet. And for the ablation of the foreground predictor, we measure the performance on the object categories, excluding the transistor. And we show that after adding the foreground predictor, we have increase in the image level score, and we have quite a lot of increase in the pixel level score. So it really helps on the pixel level score you can see here. And then finally, the comparison with the leaderboard. So you can see that even though for the image level score, we are very close to the second position, but for the pixel level score, we have a margin of about 0.058 score. And I think this is primarily because of our approach of doing the reconstruction-based method, which helps on the pixel level task. So these are some of the screenshot of the results. And before concluding, I will go over some failure cases for the 3 challenging categories. Here, the first case is the cable swap. And so during the training, when we apply the rotation augmentation on the cable, it is hard for the model to learn the different color combinations and their relative spatial relationship. Because originally in the MVTech dataset, we are not supposed to rotate the cable. So there's always green color here, blue here, and I don't know what other red color here probably. So I think for this one, we probably need to rethink some high-level feature learning, maybe some autoencoder to fix this problem. And on the screw, we noticed that we struggle for the anomalies where the anomaly is outside the boundary of the object because of the foreground predictor. So if we try to maybe dilate the foreground predictor, we can slightly improve the performance, which we did. But there is, I think, still room for improvement to cover these kind of cases. Transistor one, I think, is the most challenging one because for example, in this image, the image was originally upside down, which was a defect for transistor being in the wrong position. And when we apply the 180-degree augmentation, it actually become correct. So the model is unable to find out where the anomaly is, and that is not reflected in the ground truth mask. So maybe for this category, we need to rethink what kind of real-world augmentation we can apply. So with that, I conclude my presentation. So we propose ARNet, a feature reconstruction model that uses synthetic data and applies real-world augmentations on top to build a robust anomaly detection model. We use a foreground predictor block that was trained using the ground truth mask that were generated by the SAM automatically to make the model focus on the foreground and help boost the performance of the object categories. And also, we show that we have a high pixel and image level score on the augmented test set. And finally, we achieve a score of 0.811 on the challenge leaderboard and rank first in the position. So that makes me conclude my presentation. We also have a poster at the end, so please come to see our poster and then you can talk to us virtually. Thank you very much.
Do we have time for some questions for Babar? So anyone has a question? Nobody?
Hi, thank you for your great work. Could you please explain once again why on the transistor image this it did not work?
Yeah, so for the transistor image, so this image, the original image was upside down. These three pins were in up direction. So these pins in up direction actually is a defect because they always want the transistor to have these three pins pointing downwards. So when we apply the real world augmentations, we apply 180-degree augmentation, then we rotate it back. Now it becomes like a normal image. So if someone sees it now, you will say, oh, this is normal because the transistor in the right orientation. But the model is unable to figure it out. And when we turn this abnormal image into the normal image, originally we should remove this, this anomaly mask here because this is no longer an anomaly, we fix it. But this is not reflected here. So this becomes a challenging case where you kind of like correct the mistake by doing the augmentations. I hope it makes sense.
Okay. Yeah, I think I understand. Thank you.
Thank you.
Hey, so do you have an ablation without the foreground prediction? So what I want to know is, so you mentioned that you do foreground prediction because it kind of alleviates the issues with when you do the geometric augmentations, which kind of introduce artifacts, right? So is that the only problem it's solving, or due to, other corruptions, like you're also reducing the chance of background being? identified as
The yes. Uh, uh, so I think the sorry, let me go back. So this is the ablation that you're referring to. So originally the goal was to solve the problem that you mentioned about different orientation. But I think after we apply this augmentation, it actually helps improve the pixel level score, which is the not our target objective exactly, but it kind of like improves quite a bit on the pixel level score because we do this foreground to reweight the residual, which kind of maybe helps the model, learn the foreground area better. Yeah, so the original target was really just to focus on when you have something on the corners or on the edges of the image, but it actually helps model, do better in other areas too.
Okay, thank you.
Just a quick question. And that's
Yeah.
not related exactly for your work, but maybe on the challenge in general. So if I understand, like, do we need a data science to decide the orientation? Because, for example, maybe the rotation is not normal. So maybe the anomaly is if something is rotated. And the transistor case, you mentioned that the pin has to be in a certain way. So do we need a data science to decide how the orientations are going to be done?
I think for the this is actually something that I also think about because I think half of this challenge was us trying to figure out what kind of augmentation can happen in the in the real world, and also at the same time when we were doing the model development, we were actually thinking from the perspective of also that, okay, what kind of augmentations are generally available in the in the let's say PyTorch or Torch Vision that they will likely use to simulate them. So I think for the case of the data science, I think we can probably consider that to for this. But I think one thing I'm pretty sure is that we need different rules of augmentation for each category, I think.
Yeah, maybe I can comment on this one a bit as well, because when we were designing this data set, we had to make the same design choices. Like we had to decide which kind of transforms are we going to apply to this data set to simulate the domain shift. And we tried to make a selection of transforms that we think are realistic, that you can see in the real world. And yeah, a slight rotation of the camera angle or a slight translation is something that we think doesn't make the object in this data set anomalous, but it is something that you can see in, for example, in a production line where an object on the production line is slightly displaced. It doesn't necessarily have to be an anomaly. But yeah, of course, this is very specific to the data set. And yeah, I think in industry, it depends on specific use case if something like this is an anomaly or not. But we had to make a selection of transforms, and we decided to include these. Yeah. Any other questions? Otherwise, we'll move on to the winners of the second category. All right. Thanks a lot, Babar, for joining us this early hour. And thanks a lot for your contribution to the challenge.
Thank you. Thank you very much.
We have more live. First, I thought. Is anyone else there live to present their work?
Yeah, we have the backup people.
Yeah.
Which one is next?
Next is the number 2 of track two.
The
which is-
anomaly, MOE.
No, that's the winner.
Yeah, segment aligned features.
I think so. Yes. Yeah, yeah.
Also in the
yeah.
PowerPoint as well. I see. Yeah, right?
Yeah, yeah.
Okay, then we just need to share it. No.
I'm actually here.
Oh.
Hello, my name's Eva. Okay.
Okay, great. So yeah, then just share the screen and make the presentation live.
Okay, sure. Okay, can you see the screen?
Yes, I think so.
Okay, so shall we start?
Yes, you can start already.
Okay. Yeah, hello. My name is Ziyu Bao, and I'm excited to present our work conducted at Ruijie Networks, titled Segment-Aligned Features in Post-Logical Constraints. This work achieved second place in track 2 of the VAND 2.0 challenge. Our code is available on the project's webpage. In a nutshell, track 2 of VAND 2.0 challenge focuses on leveraging few-shot learning alongside pre-trained visual language models to distinguish between anomaly-free images and those with structural or logical anomalies in the MV-TAC local dataset. For instance, within our breakfast box examples, a structural anomaly is identified by damage to the skin of the upper orange, whereas a logical constraint anomaly is represented by an incorrect ratio between cereal, dried banana, and almonds. Existing feature-based methods have limitations. They are good at detecting structural anomalies, but not at detecting logical anomalies. To address the limitations of feature-based methods, we drew inspiration from the success of PSAD and COM-AD in surpassing these limitations through the use of semantic segmentation. Motivated by this, we aimed to showcase such success in few-shot scenarios. Our contributions are twofold. First, we have successfully demonstrated the application of semantic segmentation in few-shot settings. Second, we have shown an effective integration of segment-agnostic and segment-informed features for anomaly detection. Our proposed method focuses on image-level anomaly detection using segment-aligned features. The few-shot training paradigm operates as follows. First, from either a single or multiple training images, we randomly select an image. We use the segment anything model, SEM, to perform semantic segmentation on this chosen image. The result, a semantically segmented frame, is then stored in memory as the reference for all other training and testing images. Second, with the training images and the reference frame in place, we apply decoupling features in hierarchical propagation for video object segmentation, DEALT. This method, tailored for segment-level multi-object tracking, produces semantically segmented results that match the semantics of the reference frame. Third, we employ DynoV2, a pre-trained model designed for robust visual feature extraction to derive deep location-aware features from the training images. These features are utilized in two ways. First, combined with pixel semantics, they form segment-informed deep features, which are later used to calculate the segment-informed anomaly score during the testing phase, Second, without pixel semantics, we derive segment agnostic deep features used for calculating the segment agnostic anomaly score. Fourth, using the training images and their pixel semantics, we derive segment-informed shallow features, such as histograms of pixel counts per segment. These shallow features, when combined with the segment-informed deep features, facilitate the calculation of the segment-informed anomaly score in the testing phase. The calculation of segment-agnostic anomaly score proceeds as follows. During the training stage, we compile a memory bank of segment-agnostic deep features, which are stripped of their location information. In the testing stage, we compare the feature of each pixel to its nearest neighbor in the memory bank. The distance is measured by calculating 1 minus cosine similarity, namely, sorry?
We're back.
Okay, so I'll continue. Namely,
Can you,
cosine dissimilarity.
Nestor, can you hear me? Could you maybe, I think, when did we lost him? Like one slide back?
Yeah, I can hear you.
Yeah, just start this slide again.
Okay.
Yeah.
Okay. So I'll continue. If it's like the sound is all right.
Yeah, we can hear you again.
Okay. The segment agnostic deep anomaly scoring is calculated as follows. During the training stage, we compile a memory bank of segment agnostic deep features, which are stripped of their location information. In the testing phase, we compare the feature of each pixel to its nearest neighbor in the memory bank. The distance is measured by calculating 1 minus cosine similarity, namely cosine dissimilarity. This process yields anomaly scores for each pixel. The segment agnostic anomaly score is then determined by taking the maximum of these scores. In determining the segment-informed anomaly score using deep features, we follow a process akin to that of segment agnostic approach. The key distinction here is the incorporation of segment information. We've found through empirical evidence that this segment-informed score, when used in tandem with the segment-agnostic score, significantly enhances our ability to detect anomalies. Let's delve into the concept of shallow features, which include crucial elements such as the location of a segment, its color, the number of pixels it contains, and the mean embedding of the segment. To illustrate with a concrete example, let's focus on a segment pixel count. First, we transform a histogram of a segment pixel count into a one-dimensional vector. Then we measure its uniqueness by performing a cosine dissimilarity comparison with its closest nearest neighbor among the one-dimensional histogram vectors derived used during the training stage. The resulting cosine dissimilarity value serves as our anomaly score. Our final anomaly score is derived from a normalized weighted summation of both segment agnostic and segment informed scores. During training, we take one image as the test image and use the remainder as training images. We then carry out both training and testing processes to determine the weights. These weights are subsequently utilized in testing for summation purposes. In single-shot scenarios, the weights are naively determined manually. Now let's take a look at some of the results. Having obtained the anomaly scores for each image, we plot the density distributions of the scores corresponding to each category: anomaly-free, structural, and logical anomalies. So if the distribution of anomaly scores is distinctly separated from the loss of structural and logical scores, this indicates the effectiveness of our method. As we can observe from the density plot, this separation is indeed apparent. We have calculated the F1 max score to be 0.832 in these single-shot breakfast box scenarios. We conducted comparative analysis with WinClip, COM-AD, PSAD, and Anomaly Dino, all of which propose solutions akin to ours. The implementation of WinClip was based on the Anomaly library. COM-AD, PSAD, and Anomaly Dino were self-implemented few shop versions without the use of open source projects. Moreover, the semantic segmentation and alignment strategies employed by these methods were developed in-house, utilizing our proprietary SAM plus DEALT-based solution. Our approach achieved the highest mean score compared to the rest. We have conducted two types of ablation studies. In the first, we compared deep features with and without inclusion of segment information. Surprisingly, the combination of these two types of deep features performed better than either one alone. The underlying reasons for this require further investigation. In the second study, we examined the effect of combining different shallow features with deep features. The results did not consistently show that shallow features enhance the performance of deep features. However, further investigation suggests that this conclusion may need to be revised with the implementation of improved segmentation and alignment strategies. Our method's performance was found to be less than ideal due to inadequate segment-level alignment in DEALT. Despite extensive testing, including trials with Hungarian and nearest neighbor matching, results remained unsatisfactory. Moving forward, our primary objective remains to develop and introduce a more effective segment-level algorithm for segment alignment. Thank you. If you have any questions, please feel free to reach out, and also I'm open to questions now.
Any questions from the audience? Yep.
Hi, thank you for this great study.
Thank you.
What was the input prompt of the segment anything model?
So the input prompt is like a grid of evenly spaced points.
Okay, I
The
see.
prompt is, yeah.
Yeah, the one that is available on the platform, I guess. I mean, there are some like you can make like example inference online. Yeah, I see. Thank you.
Okay, yeah. So basically, it's an automatic semantic segmentation scheme using SAM.
Any other questions from the audience? If not, then we could move on to the winners of the track 2, which with the project Anomaly MOE. Are they live in the stream at this moment? No? All right, then I'll try to start the video.
Hello everyone, my name is Zhao Honggu from the Foundation Water Research Center at the Institution of Automation, Canada Academy of Science. Today, I'm excited to present our project, Anomaly MOE, which is our entry for the 3PR 2024 VAND Workshop Challenge. We achieved the first place in Part 2. Our approach primarily leverages the mixture of experts framework, combining the advantages of various anomaly detection methods to enhance the overall capability of detecting both logical and structural anomalies. Our motivation stems from the limitations of existing AD methods. Existing methods point to three categories. The first is VLM-based. This method compares the similarity between image features and text features that represent normal and abnormal semantics respectively. VLM-based methods typically use global features reflected by clip and focus on the global information of image, making them suitable for detecting global logical anomalies. However, their detection capability for fine-grained anomalies is relatively weak. The second is part segmentation based. This method first segments the image into multiple parts and then determine whether each part is abnormal based on features such as size, shape, and color. They are suitable for detecting part-level logical anomalies such as addition or deletions, but have weaker capabilities in detecting structural anomalies which do not affect the size, shape, and color. The last is a part-level feature-based. This type of method stores the features of normal patches in a memory. When a new patch feature is obtained from a test sample, the method determines whether the patch is abnormal based on the distance to the nearest normal patch in the memory. This method performs well in detecting structural anomalies that have never appeared in normal samples, but have limited capability in detecting logical anomalies formed by incorrect combination of normal patches. Our anomaly MOE method combines the strengths of the formation anomaly detection method and addressing their issue that each method is only effective for specific types of anomalies but not for others. Specifically, we utilize VLM per segmentation models and patch-level feature comparison models to calculate 4 types of anomaly scores at varying granularities. They are text score, global score, hard score, and patch score. By interpreting these scores, we derive the final MOE score to accomplish the AD task. Next, I will provide a detailed explanation of these 4 types of scores. First, let's talk about the test score obtained through interaction with text features. Traditional VLM AD methods require manually writing text to represent normal and abnormal semantics, which involves a significant amount of work. To address this issue, we use learnable text vectors based on COCO and train them to represent normal and abnormal semantics. When calculating the test score, we first compute the cosine similarity between the image features IG and the normal and abnormal test features Fn and Fa. Then we use the softmax value of IG and Fa as the test score, as shown in the right image at 0.6. For the global score, we extract global image feature using the fixed global encoder and a trainable linear adapter. We store a normal global feature in the global memory. During inferencing, we calculate the cosine distance between the test image feature and the stored normal features, using the minimum distance as the global anomaly score. Next is the part score. To calculate the part score, we first need to perform part segmentation. Since we cannot access the samples in the MVTech dataset beforehand, we cannot train a segmentation model for MVTech local like other methods. Therefore, we use a feature clustering method for part segmentation, referencing COM-AD. We first use the dynamic encoder to extract the feature map of the input image, and then cluster the feature in the feature map to obtain part masks. After obtaining the masks through clustering, we further process the masks, such as the filtering out the background region masks, and using the OTS0 method to calculate the optimal threshold for binarizing the masks. After obtaining the part masks, we use the mask to extract the deep features of each part of the image. Specifically, we use the pre-trained clip or dynamic encoder to get the feature map, the input image, and then use the part masks obtained in the previous step to filter the deep feature for each part. Next, similar to the processing of a global feature, we store the deep features of each part of the normal sample in the corresponding memory. We then calculate the cosine distance between the test image part features and the normal feature in the memory to get the part deep score. In addition to deep scores, we also consider geometric features such as area, number of connected regions, and color. These features help in detecting added or missing components. We calculate the area, number of connected regions, and the color of each part mask, and then concatenate these three attributes to form a three-dimensional geometric feature vector. After that, we use the same calculating method as before to get the part geometric score. Combining the part deep score and the part geometric score, we obtain the final part score. The part score effectively detects logical anomalies in different subparts of the image, such as addition or missing screws in the screw back category, or the missing red date slices in the breadth-first force category. For the patch score, we extract patch features using the pre-trained clip or dynamic encoder and train a pixel decoder for better feature representation. Then we use the same method to calculate the patch score as shown on the slides. The final anomaly score is a combination of the test, global, part, and patch scores. Different anomaly detection methods excel at detecting different types of anomalies, making the MOE score can detect logical and structural anomalies at the various levels of granularity. Our method is trained on the MV-TAC-AD, VAND, and CADSB datasets. MV-TAC-AD and VAND are two common anomaly detection datasets, each containing thousands of anomaly, normal and abnormal images from more than 10 categories. CADSB is a logical anomaly detection dataset containing images of screws and nuts. Across these three datasets, we sequentially train the pixel decoder, image adapter, and the learnable test vectors using specific functions to optimize each component as shown. We evaluate our model under 1, 2, or 8 short settings on the MV-TAC local datasets. For each K-short setting, we randomly selected K-normal samples 3 times and averaged the results. Below is the leaderboard of the challenge. As you can see, we get a UFC of 0.8184 to win the first place. In conclusion, our approach effectively integrates VAM-based, part-based, and patch-based anomaly detection methods. By using the MOE framework to combine these methods, we have developed a high-performance approach capable of detecting logical and structural anomalies at various levels of granularity from coarse to fine. Finally, there are our references. We mainly refer to Philo to implement our VLM-based method, COM-AD to implement our part segmentation-based methods, and Anomaly TPT to implement our patch level feature-based method. Thank you for your attention. I'm happy to take any questions.
All right, I think that sums it up for the contest winner presentations. Yeah. This one? This one. So I'd like to conclude with inviting everyone to our other events that we're hosting at CVPR by Intel. So the first one is the CVPR tutorial, which is tomorrow, which focuses on OpenVINO and OpenVINO training extensions. And the second one is the networking meetup, which is on Thursday. These are the maintainers of the challenge. So this is our team, Paula, Samet, myself, and Ashwin. Thanks everyone for working on this together. And this concludes it. I'd like to thank especially all the participants and the organizers of the workshop, of course, for giving us the opportunity to organize this challenge. Thank you.
Yeah. Yeah, no, I just want to share also for the remote participants. So let's see. Yes, so also a big thank you from our side actually that you organized and hosted the session, the challenge, sorry, that you did all the work and put all the effort into it, because kind of we did it last time and it was a little bit smaller and it was still kind of an enormous amount of work, and now it was even bigger, and yeah, we really appreciate it. So yes, and now we have the poster session in the other building. Just a few things on that. The first thing is we have the poster wall from 109 to 138. So in case you have a poster, just put up your poster on a free slot. We do not have a strict numbering where to put which poster. The second thing is that on each poster there should be a QR code. So in case there's just a virtual presenter, you can scan the code and enter a virtual chat, and people should be online. There is also a link on our webpage where you can, there's also a Google Sheet with all the poster names and with the links to the chat rooms. So in case this is easier for you, we have provided that as well. Anything else?
Just to say, if you do arrive to collect your poster and you find it's not at the poster collection point, it's probably because our people have already collected it in a batch to take them and put them all up, because we couldn't really differentiate who was here and who wasn't.
Yeah. Yes, and before you leave, as I said also in the morning, if you have feedback for us, highly welcome. We always want to improve. So in case you liked it, let us know. Kind of, that's always good to hear. But also in case you dislike something or something was missing from your side, if we should change anything, then yeah, let us know as well. That's even more important, I would say. So yeah, thanks for participating and see you at the poster session. Yes, I just want to leave it for a second so people can.
And a big shout out to Philip for constantly fixing the microphone every 30 minutes. But what was the issue with it? Is it just like a timer thing? Like
I had the feeling it was a timer that kind of it just went off after 30 minutes.
Maybe it's just like
In a message it would just say, because it was the output that went off. I think it's beyond this. Now it's
yeah, I think
it's not a
so,
message,
right?
it was like, finish
Like
the
like nothing moved, right? Literally.
Have the same thing.
Yeah, might as well just give them a heads up that there's some.
CVPR will pay a lot.
Yeah, yeah.
So,
Yeah, for sure. So
No,
this
VNPC,
is something.
we have one.
I mean, it's weird. Like nothing moved, right? People were just speaking virtually.
The
Like
laptop, the thing is the mic bit as well. So
yeah, exactly. And it's like not when we turned it back on, it didn't just immediately work again, right? It maybe it took a while, but first time pretty.
Excellent. Are you walking to the position or?
Yeah, I'll have a chat with you.
Okay, we can have the detailed talks, yeah. Tomorrow I can't really attend the open video session with another workshop. I'll have to request that. Regarding the technical stuff, we can find time. But I have more important question for you since you're also working with people. I'm in Portland next Monday with you, with the lab folks, trying to create a program for universities. Especially we already have contacted a couple of universities in Munich, including the and I don't know if you know it. The Technical University of Munich. Yeah, I'm also from that university, so we kind of collaborated and they agreed to start this program. I'll let you know what the program is about. So the idea is we are trying to donate a couple of GPUs, trying to source it from US and China into large GPUs. Right now I have access to like a couple of maybe 670. But the idea is we are giving these GPUs with one condition. They have the autonomy to create any program they want because that's a good thing right now. But the condition is they want to use, they should use Intel open source to it could be around anything. And I already know that you have a great reward revolving around Filipino and stuff like that. But if there's a chance, if there's an opportunity which arises that you need to give some tutorials or something like that, at least university, so that they could create a lab course, right? The condition is they have to create a lab course for the students revolving around and open source programs. Thank you. Can I just take your permission to use your contact? If I get to know more, I'll let you. But is it okay if I use your information on the slide? Because I'll be presenting on next Monday in Portland about it. The anomaly slides or no. As the tutorial slide saying we already have folks who are already contributing in giving tutorials. We just need to do the same thing once we have this lab courses just for half a day or so that they could know more about the software suite, and then they create their own master courses, lab courses basically. And once this works out, we probably have to. We're already in talks with the university. If it works out well, we'll have to expand it. And that's what NVIDIA is doing. They've been doing this for years. Yeah, exactly. Right. I have to look more critical. Yeah, of course. Yeah. I mean, yeah, I'm sure. No, you can finish your conversation probably. I'll be in the future. Okay. So yeah. See you. I haven't used it. The only time it used was when I was looking for an option. Yeah. You know what's up.
Yeah, let's go support Blush.
All right, well done again.
Yeah, thanks.
Oh, yeah, but you have to present that. Yeah.